My name is Alan Wolke. I'm W2AEW. Between myself and Pat, K2PAT, why don't you wave there, Pat? And then and Joe Zaroff, WA3NEQ. There's Joe. So we'll be your instructors here this morning. All right. So as was mentioned in the documents or the information on the TCF website, there isn't really time to teach all of this material in the time that we have. We're really reviewing the material. So I hope that you had a chance to do some pre-study on your own before we go through here. But the idea here is to run through the material, review it all, so that you can identify those things that that maybe you have a question on that we can address later on. I'll ask if you're not one of the speakers, please mute yourself. So this is our agenda. These are the materials we're going to cover. It really comes right out of the license manual, and again comes out of the KB6NU study guide that was mentioned early on. But these are the materials that we'll cover here. I'm going to be starting off here, then Pat will pick up in the middle, and then Joe will pick up at the tail end here. So real quick, what is amateur radio? It's a hobby, absolutely. It's a service, absolutely. And it's fun. That's why we're all here. And it's really what you make of it. Everybody gets a little something different out of it. And I think you'll find the same thing for you as well. So it's a way to communicate, experiment, serve, interact, and compete, really. So it is regulated, but it's not commercial. I mean, you can't use it for commercial applications like taxi services and things like that. Can't use it. Experimentation is allowed and actually encouraged. Build your own equipment and things like that. It's one of the things that I enjoy actually about the hobby, but it's not, that may not be in everybody's ball of wax. Community service. Oftentimes ham radio clubs will provide communications for things like bike races and boat races and things like that. And certainly and under emergency situations is another area. Technical learning and discovery. And there's even ways to compete. There's amateur radio contests that run that. So if you're a competitive type person, there's ways to compete as well. So that might be your cup of tea. So there really is something for everybody. So a lot of cool things to do, everything from talking through amateur radio satellites and talking to astronauts, to radio control, to just rag chewing with people and talking with people, building equipment and things like that. So you can find those things that you like and apply them to the hobby. So the first concept we're going to talk about are the electrical principles that you'll need to know to pass the exam. And again, we're not going to be teaching the materials here, and this is just enough to get you familiar with the terminology if you're not familiar with it, and understand the basic concepts so that you can go ahead and pass the exam. The first concept we'll talk about is voltage. Okay, voltage is kind of like the force that pushes electrons around. Now, anytime in any of these slides where you see something either bold or italicized, it means these are words that appear in test questions. Okay, so just make it easy to, voltage and force are things that you might want to put together. Okay, it's also called electromotive force, EMF, as another name for voltage. Okay, it's called the electromotive force. And it's measured in a unit called volts. And it's measured with a voltmeter. Okay, there might be a question that says, how do you measure the voltage? Well, it's a voltmeter. Okay, the symbol is E, standing for electromotive force. The symbol for voltage is E, but the unit symbol is volts. So like 120 volts, 12 volts, it'll be like 12V or 120V. But when we use it in a formula, the symbol for voltage is E. And another question might ask, that a typical mobile radio requires 12 volts to operate, like a car battery. The reality is it's 13.8, but the exam says 12 volts. Okay, so that's what it is. Okay. Current, that's the other aspect of electricity that we'll talk about. And the current is the flow of electrons in a circuit. Okay, italicized, that might be an exam question. Okay, it's measured in the units of amperes or amps. Okay, the symbol for it is I. So when you see it in a formula, the symbol is I, but the unit symbol is A. So if you say there's 3 amps flowing, it'd be 3A, is 3 amps. Okay, it's measured with an ammeter. Okay, so it's like amp meter, but without the P. DC stands for direct current, meaning the current flows in one direction, like from in a battery type situation. AC is alternating current, where the current flows back and forth, changing direction on a regular basis. And that's typically what comes out of your wall outlet, is 120 volts AC, stands for alternating current. Okay. So it looks like something popped up in the chat here. Okay. Let's see. Okay, thank you, Pat. Or thank you, John. So, okay, so let's see. Alternate, let me go back up here. So alternating current again is AC. The frequency is the number of times per second that the alternating current makes a complete cycle. Okay, so going from positive to negative and back to zero again, that's one cycle. How many times a second that happens, that's called the frequency of the alternating current. Okay, and the unit for that is hertz. So in the US, our line power is 60 hertz, or 60 cycles per second. Okay. Resistance is the third element of electronics. We talked about voltage being the force. We talked about current being the flow of electrons. Resistance is the opposition to the flow of electrons. Higher resistance means a smaller amount of current. You can think of it as like shutting a valve on water, or squeezing a pipe to restrict the flow of water. Okay, if you think about the water as the flow of electrons. It's measured in a unit called ohms, and the symbol is R for resistance. The unit symbol is the Greek omega symbol, okay? And it's measured with an ohm meter. So we talk about electricity, we'll talk about conductors and insulators. Right? Conductors offer very low resistance. They allow current to flow. Copper, aluminum, gold, silver, any type of metal typically is a very good conductor. Okay, insulators offer very high resistance with very little or no current flow. So plastic, wood, glass, mica, paper are all examples of insulators. So when you pick up a wire, you pick up the wire that leads to your lamp, it's typically a plastic coating on the wire, so you're not touching the wires. That's why you don't get electrocuted when you plug your lamp in, right? Because you're actually touching the insulator. Okay. So if you put all these things together, we can talk about power. Power is the rate at which electrical energy is used. Okay, it's measured in watts. So like a 100-watt light bulb, for example, that's the power of that light bulb. The symbol is P for power, and the unit symbol is W for watts. Okay, and it's often not measured directly, but calculated. And we'll talk more about this in the next slide or two. Okay. So we can relate all these terms together with something called Ohm's law. Ohm's law relates voltage, E, current, I, and resistance. And this little pie-shaped symbol is something that you ought to write down, because when you get your scratch paper to do your test, write this down. It's a handy little hint to help you with the formulas, because it shows you the relationship between voltage, current, and resistance. All right. And the relationship is such that the voltage is equal to the current times the resistance. Okay, so if you have the current, you have a known amount of current flowing through a resistor, the voltage across that resistor can be calculated by the product of those. The current is and you can just rearrange this formula to say the current is equal to voltage divided by resistance, or the resistance is equal to voltage divided by current. Now, rather than remember all three of these formulas, if you write down this simple little thing, E over IR, what you do is with your hand, cover up the quantity you're looking to calculate. For example, if I want to calculate E, I cover it up and I'm left with I times R. They're right next to each other. If I want to calculate R, the resistance, I cover that up and I'm left with E over R, right? E divided by R, actually E divided by I, or E voltage divided by current. So this simple little thing makes it very easy for you to remember these three formulas by just writing this one thing down. Just cover up the quantity you're trying to calculate and you're left with the formula to calculate it.
Alan?
Yes.
One little hint I found that helps people remember what I is. I is the intensity of the current flow.
Right.
I believe that's where it came from.
Yeah, it came from the French word intensity for current. That's why, unfortunately, it's not C for current, because we use C for capacitance. So, but that's where that came from. Thank you, Pat. So a couple of examples, and these are examples that are specific questions. You may not get these questions on your exam, but this is how they're worded. So we have 90 volts applied across a resistor, resulting in 3 amps of current. So I know the voltage, I know the current, I want to calculate the resistance, right? So I cover up R, I get 90 volts divided by 3 amps, and that gives me 30 ohms. Same thing, 12 volts applied to a circuit with 8 ohms of resistance. Now I know the voltage and the resistance. I want to calculate current, right? So E over R and calculate the current. 2 amps flowing through a 10 ohm resistor. What's the voltage that appears across that? And that's if I cover up voltage, I multiply those two together. And keep in mind that these are all multiple choice tests. The other answers in the multiple choice test will be if you apply the formulas wrong. So if you added something, subtracted something, or you multiplied instead of divided, oftentimes that's what the wrong answers will be. So just again, if you've got this written down, it's very easy to figure out which formula you need. So let's talk about series and parallel circuits. A series circuit is when the devices are really connected end to end. Like these two resistors are connected in series, right? And a parallel circuit is when the devices are next to each other. Okay, they're both kind of connected, essentially in parallel like a railroad track. Okay, in series circuits, there's only one path for current to flow. Right, current is going to flow on the wires. It only has one way to go. It's going to go through everything. So the current is the same through all of the components, right? I've got one fixed current that flows through all those components and is unchanged at the component junctions. Okay, again, these italicized words because these are words that might appear in your exam questions. The voltage across each component in this is going to be determined by the type and value of these components. So the voltage appearing across R1 and the voltage appearing across R2 are going to depend on those resistor values and the voltage. Okay. So the sum of the voltages across the components equals the voltage source. So I got a voltage source, say this is a battery here. The voltage across R1 plus the voltage across R2 will be equal to that battery voltage. So for parallel circuits like this, each component is connected to the voltage source directly. Like I can see resistor 1 has got a direct connection to this battery. Resistor 2 has got a direct connection to the battery. Okay. The voltage then across each component is the same, right? Because I got the same wire connected top and bottom here. But the current divides between the junctions. So I've got a total current that's coming out of the battery, and it's going to divide. Some of it's going to go through R1, some through R2, and then collect up at the other end. So the current depends on the component values. And the sum of the currents in each of those branches equals the total current in the circuit from the source. Okay. So for calculating power, we've got a similar little mnemonic. And you can almost think of it as a pie chart, right? PIE, power, current, and voltage. And the same type of equations here. So the formulas work the same way. So very similar to Ohm's law, where we have EIR, we've got PIE for power. So the power is equal to the product of the voltage and the current, and then you can rearrange formulas the other way. So here's a couple of example questions that you might see for power. One is, how much power is being drawn or being used by a circuit that draws 10 amps from a 13.8 volt source. So I'm looking for the power value, right? So I cover up P, I'm left with voltage times current. So I multiply those two together, get 138 watts. Okay. Now, if I've got an applied voltage is 12 volts and the current is 2.5 amps, what's the power? Well, same thing again, I'm looking for power. So I'm going to do the product. I got a 12 volt circuit and 120 watts is being consumed. What's the current? All right, so I'm looking for the current. So I cover up I get P over R, excuse me, the power divided by the voltage, and I get 10 amps. Okay, so this is the way the questions would appear for those that you would have in the exams. Okay. So let's talk about some of the math for electronics. Let's start with prefixes. We use a lot of prefixes in math because we deal with some very large and very small quantities. So the prefix milli stands for 1/1000th of something. Okay, so when we say 1 milliamp, that's 1/1000th of an amp. Okay, it can be written out in decimal like 0.001 amps. That's equivalent to 1 milliamp. Okay. Micro is just 1/1,000,000th of something. So something like 3 microvolts is equal to 0.000003 volts, right? Or 3 millionths of a volt. Okay. pico is 1/1,000,000th of something, okay, a millionth of a millionth, all right, such as, 5 picoamps would be 0.00005 microamps, right? I didn't want to do all the zeros for pico, okay, but so milli, micro, and pico, 1/1000th, 1/1,000,000th, 1/1,000,000th of a millionth, or a trillionth, okay. Going the other way, when we do multiplications, we'll have kilo, very common one that you see, is multiplying by 1,000. So 1 kilovolt is the same thing as 1,000 volts. Mega stands for 1,000,000 times. Okay, so like 1 mega ohms is the same as 1 million ohms. And giga is 1 billion times, okay, such as 2.4 gigahertz, 2.4 billion cycles per second. Okay, like your Wi-Fi operates at 2.4 gigahertz. Okay. The prefixes are often used because on different electrical quantities, like it could be for frequency, it could be for voltage, current, resistance, etc. Okay, so a couple of examples. So 1,500 milliamps, okay, is the same thing as 1.5 amps, right? Because I could divide that by 1,000, okay, 1.5 amps. 1,000 volts is a kilovolt, right? 1 millionth of a volt is a microvolt. And 3,000 milliamps is the same thing as 3 amps. Okay, a couple of bonus questions here. Okay, so 3,500 kilohertz is the same thing as 3.5 megahertz, right? Because this is multiplying by 1,000, that's multiplying by 1,000,000. The difference between those is another 1,000, right? So I can divide by 1,000 to get there. Okay, so just move the decimal point, three places one way or the other. 2,425 megahertz is the same thing as 2.425 gigahertz. Okay, because again, the difference of 1,000 between those two, a mega and a giga. Okay, but there'll typically just be 1 or 2 questions on these prefixes, so it's good to be familiar with them. So another concept that's a little bit harder to understand sometimes is decibels, or dB. It's simply written with a small d, a big B. And when we're dealing with ratios, often power ratios, we use decibels. And because it's easy to express very large ratios with relatively small numbers. Okay. And when we cascade ratios, like if we say, well, I'm going to multiply, this circuit's going to multiply the signal by 10, that's going to multiply it by 20. If I put them together, I got to multiply those things together. Cascading ratios, we got to multiply or divide, and that can be ugly. When we cascade things in decibels, we add or subtract. So we turn multiplication and division problems into addition and subtraction problems. That's one thing nice about dBs. A positive dB value represents an increase, like something is getting 5 times larger, 10 times larger, for example. A negative dB means you have a decrease, like something is getting, it's half as big. It's like divided by 2 or divided by 10. That would be represented by a negative dB number. And there's just a couple that you'll need to remember for maybe a question or two on the exam. A 3 dB change is a factor of 2. Okay, so changing from 5 watts to 10 watts is a 3 dB increase, okay, in power. It's a ratio of 2 to 1. So 3 dB is a ratio of 2 to 1. 6 dB is a factor of 4. Okay, it's like a 4 to 1 change. So a change from 12 watts to 3 watts is a 6 dB decrease, or therefore a minus 6 dB change. Again, a ratio of 4 to 1. And then the easy one to remember is 10 dB is a factor of 10. So increasing from 20 watts to 200 watts is a 10 dB increase, right? Ratio of 10 to 1. These are the ones that you want to remember, because these are the ones that you may have a question or two. And the nice thing is they kind of add up, okay? So you can see that if I just take 3 dB plus 3 dB, that gives me 6 dB. It's the same thing as 2 times 2 for 4, okay? So a combination of dB values add and subtract. So say a 13 dB change is a factor of 20, right? Because it's a factor of 10. So it's 1 and 3. So it's a factor of 10 times 2. Okay, that's why it's a 20x. All right, so with that, we'll switch gears a little bit and talk about some electronic principles and components. So the first component we'll talk about is something called a resistor. Resistors oppose the flow of current. Okay, it's kind of like squeezing the pipe, like we talked about earlier. Okay, there are variable resistors. They typically have 3 terminals and have a knob, like volume control on your radio, things like that. They're called potentiometers, or sometimes called rheostats. I'm showing these schematic symbols for these things, as well as what it physically looks like. You might only see this shaft protruding through your equipment. The rest of this is what's sitting behind the panel. Okay. A resistor's value is expressed in ohms, that we talked about earlier. Okay. Capacitors. These are some of the symbols for capacitors. These are what they physically look like. Capacitors are quite simply just 2 conductors separated by an insulator. Okay. We might say, well, what good is that, right? That, it's going to block any current that's flowing, right? Well, the truth is it blocks DC, but it actually does some interesting things for AC. Okay. But it's 2 conductors separated by an insulator. That's a capacitor. Okay. A capacitor stores energy in an electric field. So if I apply a DC voltage to a capacitor, it actually stores charge on those plates in what's called an electric field. Okay. And again, these are questions, these words might be included in a question about these components. And the capacitance is the ability to store energy in an electric field. Okay. And the unit of capacitance, the measurement of it, is called a farad. And oftentimes, like a 1 farad capacitor would be a very huge capacitor. Oftentimes, we're dealing with capacitors that are in the microfarads or picofarads type of component values. But the unit of measure is called a farad. Inductors are kind of the opposite of capacitors. And an inductor stores energy in a magnetic field. All right. And it's often just a coil of wire. These are some examples of what inductors look like. All right. From a DC standpoint, it just looks like a wire. But for AC, it actually provides some interesting characteristics. These are some of the symbols that you might see in a schematic for an inductor. And the ability to store energy in a magnetic field is called inductance. Okay, that's an inductor has inductance. And the unit of measure is called the Henry. Okay, so and oftentimes we're dealing with relatively smaller values of smaller numbers of henries. So we're talking about microhenries or millihenries typically when we're talking about actual component values. Right? So other components, switches are pretty easy to understand, and the symbols are almost self-explanatory. They're used to connect or disconnect electrical circuits. Okay. The pole is the movable part. Think about like this symbol here for a switch. You can see this looks like an open door. And that's the movable part that you're going to close. If you push that down so it touches the other side, that actually closes the switch or it opens it. So that movable part is called a pole, because you can have switches with more than 1 pole that switch more than 1 circuit at a time. The throw is the number of places that pole can go. So in this case, a single pole, single throw, I got a single pole that can only go 1 place or connect to 1 place. This guy here is a single pole double throw. This would allow me to connect a circuit this way or that way. Single pole double throw. And then you could keep adding on. Here's a double pole, double pole, double pole, double throw, double pole, single throw, etc. So again, the single pole, single throw, double throw, kind of showed them here. It just gives you some options in terms of how these switches can be configured. So fuses are something else you'll find in equipment. This is physically what they look like. You might see some of these style fuses in some older equipment. These are typical fuses that you might find in your car, for example. That's the electrical symbol. A fuse protects the circuit from overload, primarily, basically in terms of excessive current. If something goes wrong with the circuit, it draws too much current, the fuse will melt, open up, and then essentially be like a permanently open switch at that point to protect the piece of equipment. They're rated in amps, like how many amps will this fuse allow to pass? And if you exceed that, the fuse blows. Okay. Batteries, there's the typical symbol for a battery. The longer terminal is the positive terminal. Okay, the shorter terminal is a negative one, like something took somebody away. So that's why I kind of remember that. Obviously, we all know what batteries look like. Primary batteries are not rechargeable. Typically, like the old carbon zinc batteries or alkaline batteries, you use them once, you throw them away. They're called primary batteries. Secondary batteries are rechargeable. And these are your nickel cadmium or NiCad batteries, or nickel metal hydride, the NIMH. And now we also see now some newer ones, some lithium ion batteries and some called LiFePO batteries. There are other chemistries that are involved. There's a lot of different chemistries for secondary batteries. Even the lead acid battery that's in your car, that's a secondary battery. It's rechargeable. The different types have different voltages. As you know, like a little, alkaline 1.5 volt alkaline batteries and 1.5 volts. A NiCad battery is typically 1.2 volts. Okay, and other batteries will have different typical voltages. So another component in electronics are something called diodes. Okay, and there's a number of different symbols for diodes for different variations. Many of us might be familiar with a light emitting diode, right? Most of the visual indicators on equipment these days are LEDs or light emitting diodes. It's just a diode with arrows coming off of it. Okay. One of the properties of most diodes is that it allows current to flow only in one direction. Okay. And the terminals are called the anode and the cathode. The anode is the one that looks a little bit like the size letter A. Okay, you can think about it that way. And the cathode is the bar. Okay. The cathode is the one typically on the when you look at the physical component is the one that's got the stripe on the end. Okay. It's often called a rectifier, right? It only allows current to go in one direction. Okay, so it rectifies the current. Current tries to go the other way, it blocks it. So it looks like a short circuit in one direction, an open circuit in the other. Okay. LEDs are light emitting diodes. Sometimes you see them in displays, or just you might just see the portion of this sticking through the panel of your device. It's a diode that creates light when current passes through it. As current commonly used as a visual indicator. Again, these are things that might be a question or two on your exam about that. Okay, so let's talk about now transistors. We start talking about what we call active components now. A transistor is a component where the current flow is controlled by another current or voltage. So you can see there's 3 terminals here. Okay, so we might say that the current flowing from one terminal to another is going to be controlled by a third. So you can almost think of it as an electronic valve or a gate. Okay, it's often used as a switch to turn things on or off, or an amplifier. Okay, where a small change on one pin can create a big change on the others. Okay, gain is a term that's used to measure, quantify, the measure of the ability to amplify. Right, how much gain does a transistor have? Well, oftentimes, how much gain does a transistor circuit have? And it's the ratio of the input to the output current, for example, or might be ratio of input to output voltage is a measure of gain. How much bigger, the output is compared to the input. Some transistor types. There are called bipolar transistors. Bipolar transistors are made of 3 layers, okay, of semiconductor material. There are 2 basic types of semiconductor material, an N-type and a P-type. And the bipolar transistors can either be NPN or PNP. These are the symbols for those. Okay, NPN. And the way I try to remember it is if you look at the symbol for a bipolar transistor, the arrow always points to the N material. Okay, so if I've got a PNP, this is PNP. So the base is the N material, the arrow is pointing to the N. For an NPN, collector base emitter, NPN, the arrow is pointing to the N, or the emitter. Okay, so those are the symbols for bipolar transistors. Okay, again, the terminals are base, collector, and emitter for a bipolar transistor. Oops. And they're typically referred to in this fashion as what they look like. Is there a question? Okay. Some other transistor types. There's another transistor type called a field effect transistor. Okay, it's abbreviated as FET. Okay, the current through the transistor is controlled by the voltage on the gate. So the voltage on the gate determines the current flowing from drain to source. Okay, the terminals are gate, drain, and source. Oops. Again, there are various types of FETs. They'll have different symbols, but they all are kind of common in the sense that typically just like the bipolar transistor, there's a center kind of vertical bar, but typically the drain and source come off at right angles and down, whereas on the bipolar transistors, they come off at angles. That's how you kind of see the difference between an FET symbol versus a bipolar junction, a bipolar transistor. Okay. Gate, drain, and source, again, are the terminals on an FET. And that's all you really need to know for the exam. So far, we've been talking a lot about schematic symbols. I've shown a number of them as we talked about some of these components. So a symbol for a diode, a capacitor, an inductor, and a resistor, that's typically what they look like. And a schematic diagram depicts the interconnections between components that make up a circuit. Again, this is one of the questions that's on an exam. What is a schematic diagram? That's what it is. Okay. And this is an example of what a schematic diagram looks like. I can see I've got a diode, a capacitor, a PNP transistor, a resistor here, etc. Okay, there are lots of different symbols. You know, some of these you just have to memorize if you're not familiar with them, but a lot of them are just variations. Like here's capacitors. Your basic capacitor, sometimes it's shown with a curved line, sometimes it's straight. Don't really have to worry about why at this point. Anytime you have any kind of a component with an arrow going through it, that means that that component, its value is variable. Like here's a variable capacitor or a variable resistor, okay, a variable inductor. Okay, and then we've shown some of the transistor symbols here as well. Okay, so there might be one or two exam questions that actually show a schematic like this, and it might ask you what is, you know, this component or what is that component. Okay, so here's an example of what you might see. Okay, here's a very simple little circuit here. They would say, okay, component number one, what is that? It's a resistor used to limit the input current. Okay, component number two, that's a transistor. In this case, it's being used as a switch to turn on this light bulb. Okay, number three is a light bulb or a lamp, and four is the battery. Okay, and five is the symbol for chassis ground. Typically, any piece of equipment, you know, if there's a metal housing, that's called the chassis. Oftentimes, one side of the power supply is usually connected to that chassis ground. Okay. Another example, here's a simple AC to DC power supply. Got the AC line coming in, going through a fuse and a switch. So there's a fuse. There's a single pole, single throw switch to turn power on through this guy, which is a transformer. Okay, the transformer is used to take the 120 volts coming from our line and turn it to a lower voltage AC, okay, at the output. Symbol number 5 is a rectifier diode to take the AC voltage we got coming out of the transformer, turning it into essentially pulsating DC. The capacitor is going to be used to filter that. And then we've got an LED here that's as a pilot light that tells us that the power supply is on. And there's a variable resistor to control how much current is flowing through that last component, which is a Zener diode. Okay. One more example. Here's a simple output circuit of a transmitter, for example. There's a variable inductor, that's symbol number 3. The variable capacitors here, they might be used together with the inductor to create a tuned circuit. Okay. And then symbol number 4 is an antenna. So a couple of other components you might run across in an exam question here. A relay. A relay is a switch that's controlled by an electromagnet. So it's a switch that you don't control directly, but is controlled kind of like your doorbell, for example, uses a relay oftentimes. Okay. A meter. It's used to display an electrical quantity on a numeric scale to actually measure voltage or current, for example. You often use a meter for that. A shielded wire. A shielded wire is a type of wire that prevents unwanted coupling from one wire to another. Okay, so the name kind of implies that. A regulator or a voltage regulator controls the amount of voltage from a power supply. So you might see a question on a regulator. Okay, or an integrated circuit. So an integrated circuit is a component that combines many parts into one package to perform a more complex function. Like a microcontroller or a microprocessor in your computer is an integrated circuit, whereas a diode or resistor capacitor is a single component. You know, a microprocessor might contain hundreds of thousands or millions of parts in one package. It's called an integrated circuit. So with that, that's kind of all the electrical principles and properties. Maybe we'll take a quick little pause. I'll take a quick look at see if anything popped up here in chat. I'm not sure if it did. Hold on a minute. Let's kind of pop that up here. Okay, so no questions in the chat. With that, we'll move on to some radio properties. So radio waves are what are called electromagnetic waves. Okay, electromagnetic waves, again, just the name of it. They have an electric and magnetic field components. They actually have different orientations in space if you could see them, but all you need to know is that electromagnetic waves have electric and magnetic field components. And the radio waves travel through space and carry signals from transmitters to receivers. That's really what they are. Okay, you just can't see them, but they're there. So let's talk about frequency and wavelength. We talked a little bit about frequency before. Again, frequency is the number of times per second that the cycle repeats. Now, the exam might say the number of times the signal reverses, which really technically isn't true. It was written wrong. They may have corrected that, but it might say the number of times it reverses, but actually the signal reverses twice in one cycle. But even though they say reverses, they really mean repeats. Okay, so just keep that in mind. So frequency is measured in hertz. Hertz stands for cycles per second. So how many times we kind of start back at the beginning again, we're showing 2 cycles in this particular diagram. How many times that repeats per second is the frequency measured in hertz. And the wavelength is how far that wave travels during one cycle. Think about radio waves in free space, they travel at the speed of light, right? So if you're depending on how fast that you're moving back and forth, that will determine the wavelength or how far one cycle travels before this next cycle repeats itself. So the higher the frequency, the shorter the wavelength. So a couple more radio wave facts. Okay, again, they travel at the speed of light in free space. That's about 300 million meters per second. Okay, so it might be a question on that. Okay, and that's regardless of frequency, whether we're talking about signals at 770 kilohertz like your AM broadcast radio, or 104.3 megahertz on your FM radio. Those radio waves travel at the same speed of light through free space. Okay, the wavelength is shorter as the frequency increases. Okay, so higher frequency, shorter wavelength. And the wavelength in meters is equal to this simple formula. If you take 300 divided by the frequency expressed in megahertz. Okay, so if I had a 100 megahertz signal, right, 300 divided by 100 megahertz would be 3. So its wavelength would be 3 meters. So we talk about radio frequencies. We group them in bands. It's a convenient way to talk about a group or a family of radio frequencies that might behave somewhat the same in terms of propagation. And the approximate wavelength of the radio waves is used to identify different bands. And we do this oftentimes in ham radio. We'll talk about different bands by their wavelength. For example, the 2-meter band used in ham radio spans 144 to 148 megahertz. Well, you might say, well, 300 divided by 144 isn't exactly 2, right? It would be 300 divided by 150 would be 2. Well, we just round this stuff off. So it's approximate. Okay, so just keep that in mind as well. Okay, the 40-meter band spans from 7 to 7.3 megahertz. Okay, again, it's not exactly 40, but that's the closest kind of rounded number. And that's just what we do in ham radio. So we don't go explicitly to, oh, it's the 2.732 meter band, even though that's precisely correct. We just kind of refer to that as the 2-meter band, for example. Okay, so again, not always exact. So just keep that in mind. So we talk about the RF spectrum. We can talk about, RF is obviously radio frequency. The full range of frequencies are divided up into sub-ranges just for convenience, and they're given these names here. The most common for amateur radio are HF, stands for high frequency. Okay, and that's from 3 to 30 megahertz is HF. Okay, VHF for very high frequency, and if those guys, for those of us that are old enough to remember TVs with a dial on them, right? You had a VHF dial and a UHF dial. Okay, that was because those are the frequencies that were being transmitted by the TV stations, right? So VHF is between 3 and 30 megahertz, and we can see VHF TV was in there and FM radio's in there. Shortwave radio is typically HF. And then UHF is ultra high frequency, 300 meg to 3 gigahertz, or 3,000 megahertz. Okay, and that's UHF. So UHF TV was in there, mobile phones are in there, all kinds of stuff is in there. Wi-Fi is all in UHF. And then there's others like super high frequency, extremely high frequency, and then medium, low, and very low. Okay, but the ones you want to worry about for amateur radio are these three. So each of these bands have some different properties, okay, in terms of propagation, in terms of how they travel. Okay, so there's different use cases for them. VHF and UHF, those higher frequencies like very high frequency and ultra high frequency, are typically line of sight communications, meaning that not that you can visually see things, but that the radio waves themselves don't have to go around the earth. Okay, so they're typically going to be shorter distance, line of sight type communications where there's no obstacles or planets in the way of things. Okay, so and they're not reflected off the ionosphere, and they're rarely heard outside of a local area. So it's typically used for local communications. Okay, the radio horizon is where the radio signal is blocked by the curvature of the earth. Okay, now you might say, well, okay, that's just a couple of miles out. The reality is there's a little bit of bending that happens. So the earth seems slightly less curved RF. It's not that it's just the way that things are kind of worded in the exam, is that the radio horizon is just a little bit beyond the visible horizon, because radio waves tend to bend a little bit around the earth, but not a tremendous amount, but there may be one question on that. So if you may have experienced something on your FM radio called multipath, and it typically happens with VHF and UHF, because VHF and UHF signals are oftentimes reflected off of objects. Okay, so signals that are reflected off of objects, for example, let's say I've got a radio in my car, okay, and I'm receiving a signal from a transmitter, but that signal I'm getting directly from the transmitter, but I might also be getting it from a reflection off of a mountain, reflection off of a building, or even a reflection off of an airplane or something like that. And if all these signals hit my antenna at the same time, they are all traveling a different distance. They might add up with each other, or they might actually cancel each other out, depending on what's called the phase of the signal. So sometimes if you pull up to a light and all of a sudden the station you're listening to goes away, and you move up about 3 more feet and it comes back, it's all because of this multipath type of thing that's going on. So if you're affected by multipath, try moving a couple of feet. You might fix it. And multipath can affect digital signals and affect what's called their error rates. Again, there's one question on that might show up. So multipath can affect digital signal error rates. Okay. So let's talk a little more about signal reflections. Sometimes if you can't reach a VHF or UHF station, you might be able to direct your signal to reflect off of something. Like for example, if I want to have this in my car, I actually want to talk to this satellite up here. Maybe this building's in the way. If I direct my antenna to reflect off of this building, I might actually be able to reach the satellite, for example. So sometimes reflections can be your friend. Okay. So, and multiple changing reflections due to being in a moving vehicle can cause rapid fading or fluctuation, called picket fencing. Kind of like when you were a kid and you kind of yelled through a fan in the hallway and you could hear your voice get chopped up. The same kind of thing happens with multipath. When you're moving, sometimes you hear a rapid flickering in the FM radio station, for example. Okay, that can happen. Okay. So a little bit more on VHF and UHF. UHF is better at penetrating building structures than VHF is. So it's better suited for use inside or around buildings. So oftentimes guys that are using business band radios inside of a building, the plumbers talking to each other, contractors and things like that, they're typically using radios that are running UHF frequencies. Okay. You also can get something called knife edge diffraction. So if you've got a sharp object, like a sharp peak of a mountain, sometimes little radio waves can kind of bend around that a little bit and diffract around that. So even though that might be a barrier to the line of sight between a transmitter or receiver, this knife edge diffraction can sometimes work in your favor. Okay, and range is better in the VHF and UHF in the winter because you've got less leaves on the trees and you don't get the absorption by the vegetation with the leaves on the trees. So something else we'll talk about here is signal polarization. Okay. So we talked about, remember the electromagnetic waves have got an electric field and a magnetic field component. Well, actually the orientation of an antenna will affect what's called the polarization, essentially how that field appears if you could actually see it. And it's really important primarily for VHF and UHF. Vertical polarization is often used for things like repeaters, like your police and fire will, when they're talking on their radios, they're actually talking in through a repeater, which then sends their signal back out again. Those antennas are vertically oriented and therefore use what's called vertical polarization. Horizontal polarization is often used for weak signal operation, just because of the way the antennas are constructed. It's easier to get better propagation with horizontal antennas. And if your receiving antenna and your transmitting antenna don't have the same polarization, the signals will be much weaker. So if you have two handheld radios and you're talking with your buddy, and your buddy's got his radio turned sideways, so the antenna is horizontally polarized instead of vertically, the signal level will be not as strong. So you want to kind of keep the polarization the same in both cases if you can. So long distance VHF communications can happen with something called sporadic E. And this is the E layer in the atmosphere can sometimes get these clouds of ionization that can reflect the radio signals. So we said most times VHF signals are just line of sight, but they can be reflected by these ionized clouds, that can happen every once in a while in the E layer. And it's called sporadic E propagation. And that might result in some very long distance communications beyond the horizon. And typically on the lower VHF frequencies, like on 10 meters, 6 meters, and 2 meters, which is the 28 megahertz band, the 50 megahertz band, and the 140 megahertz band. Okay, a little bit more long distance communications on VHF. Sometimes fog and rain will have little effect on 10 meter and 6 meter signals. But other long distance phenomena, these are not really in the exam, but I'll just mention them. Auroral reflected signals, meteor scatter, tropospheric scatter, tropospheric ducting. There used to be some questions on this. They may not be in the exam anymore. So now let's talk about HF frequencies. These are the 3 to 30 megahertz frequency ranges. These typically are reflected off the ionosphere. Okay, so this is like shortwave radio, for example. That's why you can hear, Radio Moscow, for example, because they get reflected off the ionosphere above the surface of the Earth. And that's what enables worldwide propagation of these radio signals. Okay, and again, this is primarily for HF. So you have the higher layers above the E layer, like F layer and above, is typically what we're talking about here. Okay. So fading is pretty common because the ionosphere kind of changes, and sometimes can cause good reflections or poor reflections. Okay. And also polarization is not so important because the reflections kind of can tend to randomize or scramble, if you will, the polarization. You get these interesting things like I got somebody here in San Francisco, okay, might actually be able to talk to somebody in Chicago through this reflection here, but somebody in Denver can't hear him. So it's not uncommon that to hear somebody say, "Oh, I can't really hear you, you're too close," right? You're actually inside that skip zone. The radio wave is going right over you and coming back down somewhere else, like skipping a rock, on the lake, for example. Okay, so there's a skip distance. Okay, sometimes you can get multiple hops, but you can say, well, I can talk to people really close and I can talk to people really far, but I can't talk to people in the middle. And that's pretty common in HF. It's also pretty common to only hear one side of a conversation because you might be hearing somebody that is, in a good place for you to hear over a skip, but the guy he's talking to might be too close to you, so you can't hear him. So that's pretty common. Okay. And you get these variations in the ionosphere. So it can be broken up in all these different layers. You get this aurora, type of effects. You can get meteor scatter, things like that. But most of what we're talking about is in the F1 and F2 layers during the day, and they combine into one layer called the F layer at night. So higher bands like 10, 15, and 20 meters are typically better during the day when the sun is kind of energizing these higher F1 and F2 layers. The lower bands like 40 meters, 160 and 80 meters are better at night when the sun is gone and these F layers are collapsed down to a single F layer. Okay. And we also experience what's called an 11-year sunspot cycle. The sunspots affect the level of ionization in the atmosphere. And we're actually just on the cusp of the increase of the next solar cycle right now. So over the next 4 or 5 years, we will see improving propagation conditions for HF communications because of the increased sunspot activity from the sun. So at the peak of the 11-year solar cycle, 6-meter and 10-meter bands can provide long distance communications around the world. So but then, and you can still sporadically when we're at the peak of these solar cycles, then all the bands really come alive. So let's talk a little bit about antennas and feed lines. Okay, so I've got pictured here, coax feeding up to a pair of wires, and this is called a dipole. Then that's one of the most common and simplest antennas to use for especially HF is a half-wave dipole. So the length of the wire from one end to the other, including the break in the middle, is 1/2 of a wavelength long. That's called a half-wave dipole. They're typically horizontally polarized. When you mount them parallel to the earth, there will be a horizontally polarized antenna, and the radiation is broadside to the antenna. So like in this case, the radiation is coming right at you, not really off the ends of the antenna. So it's not where the antenna wire is pointed. It's really off the broad sides of the antennas where most of the radiation will occur. Okay. So some more details on a half-wave dipole. It's typically about 5% shorter than the free space. If we calculate that 300 divided by the frequency in megahertz, to get meters, the antenna is actually going to be a little bit shorter than that due to things like installation and other things like that. So for example, and this one might be an exam question, a dipole for the 6-meter band is typically 112 inches long. And ideally, you cut them to a particular length to make the antenna what's called resonant. Okay. If the antenna is too long or too short, it may not work as well. You make it resonant on a particular frequency you want to use and make it the most efficient. So if you want to make an antenna resonant on a higher frequency, you'd shorten it, right? Because higher frequencies are shorter wavelengths. Okay. We've talked about the formula for wavelength in terms of free space, 300 divided by the frequency in megahertz. But here in the US, since we're talking about building antennas, we're often talking about feet and inches and not in meters. So we'll use this formula here to calculate the length of a half-wave dipole. 468. Okay, easy numbers to remember, just counting by 2. 468 divided by the frequency in megahertz gives you the overall length of the dipole in feet. Okay, and that's the overall half-wave length. So obviously, if you take half of that, let me go back. So if you take half of that, it's 2, 3, 4. Okay, would give you the length of each side. Okay. So you'll also see vertical antennas. Okay, there's a very short little vertical antenna, has a couple of radials on the sides. The vertical antennas are typically built to be a quarter wavelength long. Okay, and vertically polarized. Okay, because it's a vertical antenna. And for example, a 2-meter, or I should say a vertical antenna for the 2-meter band is typically about 19 inches long. Again, might be an exam question on that. Okay. So again, the quarter wavelength, again, it's just half of that previous formula, 2, 3, 4 divided by the frequency. All right. If you remember that as the quarter wavelength formula, it's easy to just double that to get the half wavelength formula for a dipole. Okay. So high frequency antennas or HF antennas, they can be very long, right? Because HF could be as low as a couple of megahertz. So the wavelength, like say in the 3.5 megahertz band, the wavelength is 160 meters long. So even a quarter wavelength antenna would be really tall, or a half wavelength dipole would be half of that length or about half that length. That's a big antenna. Okay, so lower frequencies, the antennas can be pretty big. So oftentimes what's called loading is often used to physically shorten an antenna. Like this case is showing a coil. It's called a loading coil. It's basically an inductor that's put in series with the radiating element to make it look electrically longer. So it's physically not as long, but it's electrically longer. So it helps you to shorten what would normally be a very big or very long antenna. Okay, so inductors in series with the radiating elements, for example. So a loaded antenna is not as efficient as the full-size antenna, but it might actually be something that could fit on your property. Okay. So we'll also talk about beam antennas. A beam antenna is often given that name because it's got a long beam, okay, in it, okay, and it typically concentrates the energy in ideally in one direction, okay. A quad antenna is something that's kind of pictured here. Looks like a couple squares, 4 sides, hence the name quad. A Yagi antenna is this style of antenna. It looks like a long beam with a bunch of elements on it. That's called a Yagi. Or a dish antenna. Everybody knows what a dish antenna looks like. These are all examples of directional antennas. Okay. And the gain of a directional antenna is the increase in signal strength in the direction of the antenna with respect to some reference antenna. It might be a dipole or something like that. So you might say that this Yagi has got 10 dB of gain with respect to a dipole. So it's 10 times stronger signal than a dipole in that one direction. Okay. So we also refer to these little antennas that are oftentimes on our handheld radios as rubber duck antennas, okay, because they look like those little bits of rubber, but they actually have an antenna inside them, but we call them a rubber ducky antenna. They're flexible antennas on most handheld transceivers or HTs, okay, so it's a lot more convenient to have something that's flexible than these fixed antennas that can poke you in the eye, okay. Disadvantages are they're not as efficient as a full-size antenna because they're typically loaded, like maybe have a coil in them instead of, like we said, a 2-meter antenna, which is a common handheld frequency. That's a 19-inch long antenna. That's a pretty big antenna to be holding next to your head, right? So the antennas are typically physically shorter because of the loading, okay? And there's a good reason not to use them in a car because the signals will be much weaker as compared to being outside the vehicle, right? Because you're just surrounded by the metal of a car, it may not work as well. Okay, so a properly mounted, say 5 wavelengths antenna provides a much lower radiation angle and more gain than a quarter wavelength antenna for mobile use. So again, just one question that might appear about that. So the 5 wavelengths long antenna is going to provide more gain and a lower angle than a quarter wavelength antenna. So let's talk about feed lines. Feed lines are what we use to get signals to and from the radio and the antenna. Okay, with handheld transceivers, there typically isn't any feed line, but if you've got a radio in your car or a radio in your house and an antenna outside, feed line is what gets you there. Coaxial cable is often used because it's very easy to use, but it does require a few special installation considerations. It's called a coaxial wire because it has essentially 2 wires that are on the same axis, if you will. One wire is the shield that's surrounding the center conductor. Okay, so it's typically called a shield and a conductor, but they both are essentially the 2 conductors that are part of that feed line. They're mainly used to carry RF between the radio and antenna. The loss in a cable increases as the frequency increases. So you might have cable that, if you use it at HF, might only have a dB of loss, but at VHF or UHF might have 5 or 10 dB of loss. Okay, the higher the frequency, the more loss a cable will have. And the impedance of a feed line, okay, ideally matches the impedance of the transmitter and the antenna. Most coax that we're using has what's called a 50 ohm impedance. You don't really have to understand what that means, but just to know the terminology, okay? And ideally is that matches the impedance, the output impedance of the radio, as well as the input impedance of the antenna, okay? That will give you the most efficient power transfer from say a transmitter to an antenna is when that impedance matches. And in most cases, again, for coaxial lines, the impedance is 50 ohms. So some common coax types. Just go by these code numbers. RG58 and RG8 are the most common, and they basically just differ in physical diameter. The RG8 is going to have lower loss, but they're both 50 ohm cables. Okay, they're both 50 ohms. There's one might be physically larger than the other. The larger the cable, typically the lower the loss. So the RG58 is thinner but higher loss on the RG8. coax with the lowest loss for VHF and UHF is like an air insulated hard line. And that's these big fat wires that you see going up cell towers and things like that. What they look like inside is this. It might be, it might be pretty large in diameter. You can see from this guy holding it how big this is. But air insulation, or just a little spacer to kind of keep the center conductor and the outer conductor separated, those are the lowest loss air insulated hard lines. So what are common coaxial failure modes? One is moisture contamination, right? If you get any cracks in the insulating jacket, water can get in there and corrode the copper, okay? Or water can get in at where you have the connectors if you don't properly seal them, and that can corrode the copper. So the jacket, or the outer insulator of the coax, if it's going to be used outside, needs to be UV resistant to prevent cracks and therefore prevent water contamination. An air core coax requires special techniques to ensure that no water or moisture gets into where the air insulation is. Again, it's properly sealing where the connections are made primarily. Okay, so let's talk about RF connectors. What are the connectors that we're using at the end of the coax? So these connectors shown here are what are called PL259. Okay, it's most common for HF frequency use. Okay, for 3 to 30 megahertz, the PL259. It's often called a UHF connector, but it's not suitable for UHF. Just a bad name. But the technical name for it is a PL259. It's not suitable at higher frequencies. Okay, the N-type connector, which is this one shown here, is typically most suitable for signals, even below 400 megahertz, but certainly above 400 megahertz, the N connector is more efficient and more common. The PL259 is not suitable for those frequencies. Again, we have to take care to seal against any water intrusion, okay, to prevent loss in the feed line and that type of thing. So we want to be sure to use a sealant of some sort, like a sealing tape or something where the connector connects to an antenna, for example. Okay, and you want to keep them tight. Loose connections can cause erratic SWR readings. We'll talk about what that means in a moment, but that could be an exam question. You want to make sure your RF connections are tight so you do not get erratic SWR readings. Again, we'll talk about that in a minute. So let's talk about what SWR is. SWR stands for standing wave ratio. Okay, and it's a measure of how well matched the load, or an antenna, for example, is to the transmission line. Remember, we said that we want the transmission line, if it's 50 ohms, we also want the antenna to look like a 50 ohm impedance. When you have that good match, you're going to have a very low SWR. Okay, so what happens is if the antenna or the load is not matched to the transmission line, you can actually have some energy reflected back. It's kind of like it's kind of like if you see a wave coming in and hits a seawall, the seawall bounces that wave back, and you see the wave going in the opposite direction. That reflected energy is going back because the wall doesn't absorb that energy. All right. So in the case of RF, if the antenna is matched to the feed line, it absorbs all the energy coming from the feed line and nothing gets reflected back. So if nothing's reflected back, you get a very low SWR. Okay, so low SWR is needed with coaxial feed lines to get efficient power transfer and to minimize losses. Okay, and power that's lost in a feed line is converted to heat. Okay, so when again a question might ask, something about, if power's lost in a feed line in the form of what? Might be heat, and it might be a couple of other answers there, but that's a question that might appear on your exam. Okay, so how do we measure SWR? There's a bunch of different meters and things that can be used. So SWR is typically measured with an SWR meter. Oftentimes it'll be called VSWR, okay, or voltage standing wave ratio. Okay, so the SWR meter is connected between the transmitter and the feed line, okay, or the transmitter and the antenna, or the feed line and the antenna, somewhere in that line. Okay, you could also use something called a directional watt meter, and that's this example here. A directional watt meter can measure power in both directions, the forward direction and the reverse direction, or therefore the forward power and the reflected power. Okay, and then you can from that calculate SWR, but the SWR meter will do it for you. So an SWR of 1 to 1 is considered a perfect match, or 1.0 to 1 is called a perfect match, meaning that all the energy is going to the load, nothing's getting reflected back. An SWR of 2 to 1 is where most solid state transmitters will enable their own protection circuits to cut their own power back to protect the output amplifier, to protect the output transistors. Because any energy that's reflected back from the antenna goes back into the transmitter and gets dissipated in the transmitter, and it may not like it. So most solid state and modern transmitters, if they see more than a 2 to 1 SWR, will start cutting their own power back as a self-protection measure. Okay, an SWR of 4 to 1 is worse than, means there's a pretty large impedance mismatch. And these are some of the examples that might appear on some questions. Was there a question I heard? Okay. And also you'll find that there's an instrument called an antenna tuner, often called a transmatch, that is used to match the antenna system impedance to the transmitter. So in the case where you don't have a perfect match, maybe because of the design of the antenna, or even just, because not all antennas have got a perfect match to the transmission line, you will use what's called a transmatch or an antenna tuner to adjust the impedance that's seen by the transmitter, okay, and allow it to deliver full power into the now tuned antenna system. Okay, so a couple of more measurements. So there is an instrument called an antenna analyzer. There's actually a lot of different varieties of these. An antenna analyzer is commonly used to measure SWR. So you don't even have to use your transmitter. You can just use the analyzer itself. It also can measure the antenna's resonant frequency, right, where it's matched the best. So that might give you some information about when you want to, lengthen it or shorten it, for example, to make it match the frequency you want to use it on. It also can measure things like capacitance and inductance, which are component values. So there's also an instrument called a dummy load. A dummy load is just a big 50 ohm resistor with a lot of heat sinking capability. And what this allows you to do is to do some testing with your transmitter without radiating a signal out into the air. So if you want to tune up a transmitter, get the power adjusted right, things like that, you can, instead of connecting to your antenna, you connect up to the dummy load. It provides a non-inductive good load for the transmitter to throw its power into without putting the power in the air, so you don't interfere with somebody. So the dummy load is a non-inductive resistor with a heat sink. Okay, again, these italicized terms might be terms that are in a question on your exam.
All right. So we're starting on time. Name is Pat. Call sign is here on the shirt, K2 Pat. And it's my ARRL short sleeve shirt, unlike Alan's long sleeve shirt. So that's our uniforms when we're doing ham things. Not required, but eventually you'll want the bling. All right, so Alan showed us how we got propagation. And we've got variable propagation depending on frequencies. So that's the radio signal. Now, what's on your radio signal? On your radio signal, we want to transfer information. That information gets transferred with modulation modes. How do we modulate the radio signal? The original basic types were either AM or FM. And of course, Morse Code, or CW, was the original, the granddaddy of modulation, and that's just switched it on or off. Switch the signal on and off. So the modulation here represents a low frequency like a voice. The AM or FM modulation here, they represent some high frequencies or some very high frequencies, like 5 megahertz or 10 megahertz or 150 megahertz. So the AM signals, they're not exactly to scale, but they shift the amplitude up and down with response to your voice. An FM signal keeps the amplitude steady, but squeezes the frequency in or out with respect to your voice. So that's frequency modulation, amplitude modulation, frequency modulation. What you'll see on some modern equipment, some modern transceivers or modern test equipment, are the pictures below. The one below here is called a waterfall display. The waterfall display, if you move your cursor, the diamond, to the signal you want to listen to, it's right here. So your red diamond over the green bar, that translates to text. You'll see the other half of this screen will show your conversation with someone else. It'll show your conversation with someone else in the version of text back and forth. I'm losing control of the screen here. Now the lower right-hand picture is a different display on different equipment. On the left, it'll show compressed digital signals. Might take up 4 megahertz worth of bandwidth. And yet, if you use the analog version looks a bit sloppier, takes up 13 megahertz of bandwidth. So what you do in modulation will affect the modulation signal. Well, the modulation will affect the broadcast signal, taking up different amounts of bandwidth. So bandwidth is a very limited commodity. Luckily in ham radio, we have tremendous amount of bandwidth, but there are still times when you want to fit more signals in a space and you have to conserve your bandwidth. So digital is one way to do that. Looking particularly at FM modulation. FM is frequency modulation. It's most common on VHF and UHF repeaters, which is where you will probably end up starting as a technician. It's also used for VHF packet radio transmissions. Packet radio is like text. It's one of our earliest versions of ham radio text after Morse code. And then we've got the AM modulation. The AM modulation shifts the amplitude. You've got the radio frequency, the carrier, the modulating wave, your voice. AM is one of the simplest modulation modes. You modulate the signal strength with your voice. And when you do that, you will take up the bandwidth as shown. The energy is present at the carrier frequency. That's the frequency in the center in the lower diagram. That's the carrier frequency, and sidebands on both sides of the carrier. So when you modulate with AM, you take up twice the signal that you would in your voice. You have an upper sideband and a lower sideband. You can cut out one of those sidebands and cut out the carrier. And that's called a single sideband. Single sideband is a form of amplitude modulation where it's concentrated in one sideband or the other. It gives you increased distance, and it's used for weak signal contacts on VHF and UHF. For example, on 2-meter sideband, you can talk from Philadelphia to Boston, at least in this neighborhood. And it would take several repeaters to do that on FM. So you can talk directly using this weak signal mode in upper sideband or lower sideband. Now, most of the technician frequencies will use, the convention is to use upper sideband, USB. The advantage of SSB properties are it has a narrower bandwidth than FM. It's typically 3 kilohertz for a single sideband versus 5 to 15 kilohertz if you were FM. And the picture below shows where your voice occupies. Your voice, your audio frequencies on the left might go from 300 to 3,000 hertz. This is a convention that includes most voices, most usable characteristic of most voices. It might not be called high fidelity, but it's useful to standardize on the amount of sideband you're going to occupy. So when you put that over on the right, you modulate that on a carrier signal, you get an upper sideband and lower sideband. You can take away the power you've wasted on a carrier, take away the power you've wasted on a lower sideband, concentrate it all on upper sideband, you take up less space, and the signal is more powerful. Now, one of the narrowest bandwidth, especially as far as the test is concerned, is Morse code at 150 hertz. Not kilohertz, but hertz. That is very narrow. And of course, it varies depending on how fast you're sending Morse code. The faster you send the Morse code, the more space you take. But its nominal value is 150 hertz. The Morse code we use is called International Morse Code. That is something that would be possibly on your test. CW can be sent 3 different ways, at least 3 different ways. You can use the straight key, which is shown in the picture. You can use an electronic keyer, which is a bit fancier. And you can use a computer keyboard. So when you're using a computer keyboard, the table on the right, the International Morse Code, as you type a letter, it sends out those characters, that modulation on your signal. Although some people use that, most CW operators love to copy in their head. Their experience, they've developed this skill to copy Morse code in their head, and they can go faster than the computer. Amateur television signals. That's another modulation scheme. The analog fast scan television signal on 70 centimeter band, it's 440 megahertz or so, takes up 6 megahertz of bandwidth. That's a lot of bandwidth. It's the same as the television broadcasters used to use 20 years ago. And the standard is called NTSC. That refers to the analog fast scan color TV signal transmission. So the old analog television signals were called NTSC. That's a name to remember for the test. Digital modes. Digital modes, usually using a computer and radio to communicate. You tie your computer to your radio as shown in the picture, and then data is sent back and forth. The data sent back and forth can be typed by hand or pre-formatted as information, such as lists. The Red Cross would like to have a list of how many people are in their shelter. This data can be sent back and forth. Technicians can use data transmission on 219 to 220. It's a dedicated portion of the 220 band that must be data only. And it's part of part of our national network for data. Some digital modes use parity. That's an extra code element used to detect errors in reception. In other words, when the message is sent, every 1,000 characters or so, you can check the byte count. If the byte count is correct, then you proceed. If the byte count is incorrect, you get an error message and probably resend. But the extra code element used, it's a bit of overhead, but it ensures that your message got through correctly. Examples of digital mode are packet. That's where they send data in packets of maybe 1,000 bytes at a time. IEEE 802.11, 802.11, that is Wi-Fi. JT65, that is a special digital mode given to the ham radio community by Joe Taylor. JT65, we'll talk about him later. And PSK 31. PSK is phased shift keying. It shifts that carrier signal back and forth just by a little bit. And that shift designates a 1 or a 0. So you can get very, very narrow bandwidth down to 31 hertz. 31 hertz worth of signal shift can be used to transmit messages. Slowly, but it still transmits digital messages. And then MFSK, multi-frequency shift keying. Instead of shifting 31 kilohertz space, you take multiple spaces, multiple frequencies, and shift those. MFSK. This is a setup for packet radio. It's one of the first digital modes, data grouped and sent in packets. Packets are smaller bytes, such as 1,000 bytes. Every 1,000 bytes, you send a packet and get acknowledgement that it's correct. Packet radio includes a checksum, which permits error detection. It includes a header containing the call sign of the recipient and automatic repeat request in case of an error. If your checksum is not right, you issue an ARQ, automatic repeat request, and the packet goes out again. It's all automated. APRS. APRS uses packet radio schemes, but it's an automatic packet reporting system, also known as automatic position reporting system. You can tie your radio to a GPS receiver, shown in the picture. The blue stuff is part of your GPS receiver. Ties to a radio, and because it may be as simple as a walkie-talkie for the radio, it may be a more powerful base station. The other thing in that picture is a battery. The red and black wires go to a battery. So that's what you can use to set up a GPS packet reporting station in your home or in your car. You get real-time tactical digital communications along with a map showing location of stations. So again, APRS includes these bold letters and the italicized letters in the questions. We have, at least in Princeton Red Cross area, we have an APRS setup. And the computer and the screen can show you what you need to know about the station's broadcasting. Could be set up as a map with the global positioning system, or it could be just text messages, either way. PSK is phase shift keying. Phase shift keying. shifts the phase. As I said, you take your carrier, you move it a little bit this way, a little bit to the left, a little bit to the right, and that contains information by shifting the phase. It's a popular HF digital mode. And PSK31 is a low rate data transition. The picture shows typing going back and forth, one station to the other, and that is deciphered from this waterfall display below. The information passed back and forth. You can probably see the red dot there, the red diamond says we're following that signal, and that signal, no matter how weak it is, seems to be getting through. One of the other advantages of digital signals, they can be made to work on very, very weak signals, stuff you'd have difficulty hearing if it was a voice. DMR. DMR is another digital technique. It's very popular with technicians because it occurs on VHF and UHF frequencies that technician privileges include. It multiplexes, because it's digital, instead of taking up all 12.5 kilohertz, they can have 6 1/4 kilohertz for one signal and 6 1/4 kilohertz for the other signal. It multiplexes 2 signals on one channel. How do we share those 2 signals? Well, they're shared on virtual channels. In other words, the A channel and the B channel can be broken up into talk groups. One example is in this area is you can have a talk group that's South Jersey. You can have a talk group that's North America. You can have a talk group that's the tri-state talk group. You program your radio for that particular group ID in order to join in any one particular group. Weak signal modes. Weak signal modes, if you send a signal to the moon and back, unless you've got a giant dish antenna in your backyard, your signal is going to be somewhat weak. If you bounce a signal off the moon or any other weak signal that you're trying to use to communicate, Joe Taylor has invented a great deal of weak signal examples. So WSJT is a weak signal done by Joe Taylor. He's a Princeton physics professor. He's very well accomplished, and he's loaned his software and his experience to the ham radio community. He's a great friend. He's in Princeton, and he's published a lot of software to help us with weak signals. One example is the FT8. FT8, go again. I'm sorry. FT8 is one of his protocols where you transmit messages in 15-second intervals. So a full communications might take 1 or 2 minutes, but it still gets through no matter how weak it was. There's an FT8, FT4, and there are several other pieces of software where Joe Taylor and his partners have come up with all new digital communications methods. So that's our digital world. One more digital world, and that's mesh networking. Mesh networking uses Wi-Fi frequencies, which are typically 2.4 and 5.8. we share those with the rest of the world on Wi-Fi. The frequencies at 3.4 the frequencies on 3.4 gigahertz are in between. We might use those for linking various regions of the country to the rest of the country, the backbone network. They are in transition right now because the FCC is shifting some of those frequencies around. But our mesh networks are designed to get in on Wi-Fi and go across the country. So this is a project called the Amateur Radio Emergency Data Network, AREDN. It uses Wi-Fi hardware and modified firmware. In other words, if we want to use, instead of half a watt coming out of our laptops, if we want to use 10 watts, we're allowed to do that. But we have to modify the hardware that is used for mesh networking. Okay. So our next topic is safety concepts. Were there any questions on the previous topics? Okay, we'll move on. Safety concepts. Because ham radio involves few hazardous things, you really should know about safety concepts to keep yourself and your family safe. You don't want to burn your house down. You don't want to get hit by lightning. There's all sorts of things to be concerned with. AC power, hazardous voltages, fuses, circuit breakers, battery safety, antenna and tower, power lines, and RF safety. General electrical safety. Because you're playing with electricity, it's easy to come in contact with dangerous voltages. What's the definition of a dangerous voltage? Anything over 30 volts. You know, if you have a car battery, that's not a dangerous voltage. It can still be dangerous. We'll talk about that later. You got a truck battery at 24 volts. It's not a dangerous voltage, but it can still have dangerous currents. But you can get a shock at 30 volts. And actually your body can be killed by having 100 milliamps flowing through the body. If you have 10 amps flowing through the body, your body can be seriously fried. So why is 30 volts a hazard? This is where they said that you can start having a problem. You can be electrocuted on 120 volts. You can be electrocuted on 90 volts. If you're standing in water and you get hit by 40 volts, it's not as likely to cause death, but it's still a possibility. If you're sitting on a ladder and you touch something at 48 volts, if you're touching a telephone wire and the phone rings, that goes up to 140 volts. You could fall off the ladder. So dangerous shocks start at 30 volts. The international safety standards start at 30 volts. Anyway, how does current hurt you? It can heat your tissue. Heating tissue can give you a burn. It could damage internal organs, disrupts the electrical functions of the cells. It can give you involuntary muscle contractions. Back in the days when electric drills were made of metal, when you are squeezing the trigger on an electric drill, you get hit with a shock and you squeeze tighter. It gets worse. You can't let go. So the involuntary muscle contractions also have their dangers. So all these three things, three issues are what can be on the test: heating the tissue, disrupting electrical function, and involuntary muscle contractions. Let's see, AC power safety. That's a 3-prong plug. Three wire outlets and plugs are safer than other types. Third wire is called a safety ground. The safety ground is often connected using a green wire. If you're an electrician, you know that there's one exception to that. That could be a bare wire. But anytime you see a green wire, it's supposed to be the safety ground. Don't leave it out. Don't let it break. Good ways to guard against electric shock: use 3-wire cords and plugs for all AC equipment. Connect all AC powered equipment to a common safety ground, and use a circuit protected by a ground fault interrupter. These days it's called a ground fault circuit interrupter, GFCI. Those are required in properly wired houses for any outdoor circuits, any circuits that go to concrete floors, such as the basement or the garage. So those should be there, and if they're not there, consider adding those. Have an electrician do it, or learn how to do it yourself. Fuses and circuit breakers. As Alan said, a fuse will interrupt power in case of an overload. Always replace the fuses with the same type and rating. These little glass fuses are not unlimited. You cannot use those on 480 volt circuits. You can only use them at either 32 or 250 volts, as it says on the label. Always replace fuses with the same type and rating. Putting in a 20 amp fuse in place of a 5 amp fuse can cause a fire from excessive current flow. If you have a short that's always blowing your fuse, don't take out the 5 amp and put in a 20 amp, fix the problem instead. You could have a fire. Always include a fuse or a circuit breaker in homemade equipment. Fuses in 120 volt AC circuits are used in the hot lead. Never put a fuse in the common lead or the ground lead. Okay. Another danger in working on equipment. These blue things called capacitors are, they store energy. They can store enough energy to hurt you. So before you work on equipment, disconnect the power. These capacitors can store energy, store charge, and shock you, even after it's been disconnected. You might disconnect, shut it off, and wait 10 minutes before you go to work on the equipment. Make sure the charge that's stored gets bled away until it's safe. Now, the pictures here are blue. When Alan showed pictures of capacitors before, they also had a black one. So that's just a plastic sleeve. It can be blue, it can be black, it can be gray, it can be yellow. But capacitors can all store energy and shock you. So they store charge, they can shock you, and it's best to work with one hand. Don't lean on the metal cabinet and touch the positive end of a capacitor. Don't touch either end of a capacitor until it's been safely discharged. Okay. All right. Battery safety, 12 volt batteries, 12 volt lead acid batteries, several hazards. One is explosive gas can collect when they're being charged. You should not charge them. You should not charge them in the house. If you do charge them in the house, have a vent nearby. Make sure that the gas does not collect there. Gas is hydrogen. Hydrogen is explosive. Shorting terminals can cause burns, fire, or explosion. So the 12 volts is not a safety hazard by itself, but the immense amount of current, hundreds of amps or thousands of amps on a short circuit, can come out of that battery. That could cause burns, fire, or explosion. If you charge them too quickly or discharge them too quickly, they overheat and give off a flammable gas or can explode. So one way not to short a terminal is use one wrench at a time, keeping it away from all the metal around the car. Take the negative terminal off first, not the positive terminal. Take the negative terminal off first, and be careful with any other metal, incidental metal on your hands, like wedding rings. Take the wedding rings off before you go to work on a car battery. You could end up with a severe burn on your finger. All right. If power is out, you can recharge your 12-volt battery by connecting to a car battery and running the engine in a well-ventilated area. So many of our radios work on 12 volts. Some people use a 12-volt battery as backup power. These are the hazards to be aware of. Antenna safety. Look for and stay clear of overhead electrical wires. Keep 10 feet of clearance to power lines, even if the antenna should fall. Never use a utility pole as a support. Don't climb the power poles in front of your house or anywhere and put your antenna on it. It's not your property, and it's not safe for you to put an antenna. What's wrong with this picture? So, is there anybody who wants to tell me what's wrong with the picture, or maybe everyone's on mute?
Too close to the power line to start with.
Mhm.
Yes. If that tower crumbles,
Hits
in
the
a very
house.
strong wind, it falls on the power lines, and the power lines are connected to your antenna, go right into your house and can cause a fire or electrocute you. Either way, it's not good. How many volts are on the power lines?
Depends
Dangerous
where you are.
voltage. Yeah, there are dangerous voltages. In every neighborhood, you can either be 120, 240 going to every house, or the lines above that, the lines near the top, are at least 7,200 volts and up. So the antenna could put 7,000 volts into your house, which will fry you to a crisp and burn out half of the appliances in your house. So make sure that you're 10 feet away from just about any power lines. Okay. Anybody recognize those two ladies?
Lucille Ball.
Yeah. Lucille and Ethel. Sure. So position the antenna so no one can come in contact while you're transmitting. So they've come in contact. Well, they're not supposed to be there. RF burns are painful and dangerous. They can burn the outside of your skin. They can burn the flesh inside. Just keep the RF away from anybody who might be able to reach it. Some things to do are to put up fences around your tower. Put up climbing gates around your tower. And of course, if someone's climbing on your roof, a flat roof is somewhere that someone can easily walk onto a flat roof. Unlike Lucy and Ethel did there. How do you do tower work? You use a gin pole to lift sections or antennas. Now, if you're not using a crane, you certainly can't lift that tower piece over your head unless you have something above that point, like a gin pole. Always use a climbing harness. Everyone wears a hard hat and safety glasses. Anybody who's working near you should have a hard hat and safety glasses, or you keep them out of the area. When the tools fall out of your hand, the people below need to wear hard hats. And never climb alone. If you get stuck in the tower, you fell halfway off the tower, or you fell to the ground, never climb alone. Crank-up towers must be fully retracted before climbing. A crank-up tower is a telescopic type tower. You can crank it up, crank it down. You must bring it all the way down before you climb it and change antennas. I mean, halfway down means the thing is going to be rickety. And use safety wires in turnbuckles to tension the guy lines to prevent loosening. A turnbuckle could loosen with time. You don't want it to loosen. You put a safety wire in there so it always stays tight. Tower grounding. The tower is a big lightning rod. It may be only 10 feet taller than your house. It may be 100 feet taller than your house. It's still, when the lightning comes, you don't know where it's going to hit, and there's a good chance it's going to hit your tower. You must consult with the local electrical codes. There's a national electrical code updated every 3 years, and at the same time or 3 years later, local building codes generally get updated to match the National Electric Code. But in any case, they've determined what's safe. You must follow those rules. When the building inspector comes to watch you put up your tower or inspect after you're done, he's going to want to know these things. Show me the ground rods. Show me the size of the concrete that you put down there. So good practice would be to put separate 8-foot ground rods for each tower leg. You got 3 tower legs, there should be 3 ground rods out there. Bond all the metal together, all the legs and rods, bond those together with fat straps or structural steel or structural aluminum. The tower legs are all welded together, but they must be all connected together so lightning doesn't come down and start to jump all over the place where it's not supposed to go. You want short and direct connections. The short direct connections avoids lightning jumping out of the way. Avoid a sharp bend. Now, I've been in a lightning lab where you simulate lightning. I've watched when you run the ground wire directly, the lightning tends to follow it. You should put a sharp bend in that so it looks neat. The lightning jumps right off the ground strap and goes where it wants. Doesn't follow where you put the ground rod. So avoid sharp bends, and all feed line lightning protection should be mounted to a common plate and connected to an external ground. That's what the picture shows. The second picture shows all of those antenna connections go through a lightning protection panel and the lightning protection devices, which all get grounded together. Now, RF exposure. When you're using high power, you are required to perform an RF exposure evaluation. Even though VHF and UHF are non-ionizing radiation, you must do a safety evaluation. This is something you sign when you sign for your license. You have to sign that you will do an RF exposure evaluation to make sure that people don't get microwaved, people don't get hurt by this non-ionizing radiation. If you're in a nuclear plant, if you're in Chernobyl, that's called ionizing radiation. That's different. Our radio waves are non-ionizing. That's on the test. On VHF, a rule of thumb is you can run up to 50 watts at the antenna without performing an exposure evaluation. This is for the purpose of the test. They're constantly updating the rules. So you should check the rules and do your evaluation and know when you're going to be in trouble. Suppose 50 watts is safe. You want to put 100 watts out. What do you have to do to make that safe? And the 50 watts, PEP, peak envelope power. All the waveforms we've seen of RF carrier so far show either straight amplitude or moving amplitude. The moving amplitude, the ones that go up and down, you have to measure the peak envelope. That's the peak envelope power. So how do we do that? RF exposure evaluation can be performed by calculation based on the FCC Bulletin 65. FCC Bulletin 65 is an important number to remember. That should be on the test. OET is Office of Engineering Technology. So the FCC, you go to the fcc.gov website, you can find Bulletin 65. And you follow the steps that they give there. Now, they've been updating that for years. The current supplement B, is what you would have to look for to find out what the latest methods are. But for the test, you just have to know Bulletin 65. You can do a calculation based on computer modeling. Good luck with that. You really want to do it according to the FCC's rules. Or you can measure field strength using calibrated equipment. So those are the three methods. And those are the three methods that the FCC would accept. Now your RF exposure, duty cycle. Duty cycle is the percentage of time the transmitter is transmitting. You know, the picture you see on the right is a very low duty cycle. You transmit only during the blue bars. That's less than 10% of the time. So the duty cycle is also factored into your exposure. It affects the average exposure level. Duty cycle affects the average exposure level. So if theoretically you're transmitting only 10% of the time, then your exposure is reduced to 10%. That's nice, but in general, we transmit about 50% of the time. Somebody talks for a minute, we talk back to them for a minute. So the best you can estimate is 50% of the time. And if somebody is going to talk for an hour, well, you better consider that duty cycle to be 100%. But that's one of the factors affecting the exposure is duty cycle. RF exposure limits. RF exposure varies with frequency. The human body absorbs more energy at some frequency than others. The 50 megahertz band has the lowest permissible exposure limit. In other words, our bodies are most sensitive to the 50 megahertz band. It has a maximum permissible exposure limit that's tighter than most others. Factors that affect exposure are the frequency and power level of the radiated field, the distance from antenna to person, and the radiation pattern of the antenna. The antennas you see in that picture are cellular antennas. They're on a roof. They're made to shoot their signal outward, away from the center of the building. So if those are transmitting, say, 10 watts, they might be multiplied by a factor of 10 because all the energy is focused outwards. So you might have the equivalent radiation of 100 watts if you're within, say, two feet. So because the antennas can concentrate your signal, that's what's that's one of the factors. The distance to the antenna, the radiation pattern of the antenna, and the frequency and power level of the field. To keep exposure safe, you can relocate the antennas, move the antennas up in the sky away from people. You can lower the power level. You can transmit less. If you're operating digital, you can cut the duty cycle way down. And anytime you make a change in your station or antenna setup, you should reevaluate. This requirement to keep things safe is ongoing. Anytime you make changes, see that it's safe. You might even want to keep records if you did some calculations or did some studies, or you quoted something out of Bulletin 65. Keep records. So when the FCC asks for your records, are you really safe and how can you prove it? You've got the data that you examined. Okay. Now, I think this is a new topic, station setup and operation. It's a very good time to see what we do next. Are we ready for lunch? Alan?
Yeah, I'm looking, it's 11:20. Why don't we go till about quarter of? Because I think, or maybe even 20 of, go another 20 minutes or so. Because I think that what that'll do, that'll take us to 20 of, and then that'll give folks time who haven't registered, time to register and get that done before noon. And then we'll have lunch and we'll get together maybe at 12:15, 12:20 to get started again. So why don't you go till about for another 20 minutes or so.
Okay.
All right.
Thank you. All right. Now, station setup and operation. The station setup doesn't have to look this complex. People have asked me for years, what does my station look like? And I show them. That's what my station looks like. A radio and an antenna. Very often I would unscrew the antenna, screw in the antenna that was in the car, and operate this little radio from the car. Little radio is 5 watts. In most areas of New Jersey, 5 watts is enough to reach many repeaters. Of course, you do better with a mobile radio. Then there's your base station radio at home. You can have all this equipment or you can have less, but it involves all these components: station accessories, dealing with interference, grounding, operating controls, station equipment, troubleshooting, and repair and testing. Okay, station accessories. Your power supply. At 12 volts, you really need heavy gauge wire to avoid the voltage drop that prevents voltage drop that would cause improper operation. Minimum current capacity, transmitter efficiency, receiver and control power circuits, control circuit power, regulation and heat dissipation. So all of these facts could be put together in a question. And the idea is, if you need a lot of current, your wires should be heavy duty. At 12 volts, which is most of our equipment, at 12 volts, the wires should be much, much heavier than house wiring, because that's 120 volts. They can afford to lose more in your house wiring than you can afford between your power supply and your radio, if it's a high power radio. The power supply shown here is a modern high efficiency switching power supply. It's a lot easier to deal with than a 12-volt car battery in your house. All right, headphones. Headphones are used to copy noisy signals. I use that many nights on the shortwave bands. It helps a lot. Microphone. Microphone includes a rig connector and a push-to-talk switch, sometimes power for the microphone. So your connector brings power into the microphone if necessary, and it includes your push-to-talk switch. So on your microphone, in general, you need to switch from receive to transmit with a push-to-talk switch. And sometimes your microphone needs power to work. Computer in the ham shack. You use computers for many things: for logging contacts, for looking up info, for sending and receiving CW, and for generating and decoding digital signals. One of the things you might look up frequently is QRZ.com. QRZ.com is where you look up the call sign and the location of people you've talked to. Digital mode accessories. For digital modes, one of the essentials for packet is a terminal node controller. It converts ones and zeros to audio tones. For RTTY, RTTY is radio teletype, or PSK31. Those are some of your digital modes. This can also often be done by the sound card in your computer. So the sound card in the computer very often works with the available software, so that you don't really need a TNC. It's always good to have some sort of interface device in between. It's easier to adjust and connect if you've got all the connectors available in your TNC, rather than try to put all that stuff into your computer USB port. Anyhow, it provides audio to the microphone, converts received signals to digital. Often an audio interface is used to adjust the audio levels and provide some ground isolation. So those interface functions are provided by a TNC or some other interface device. Interference killers. Ferrite chokes. Ferrite chokes help to minimize some interference. That's the first step. It's not always enough, but it's usually the first step to get interference from your audio power supply and other cables going to your computer to keep that out of the radio. You can reduce RF flowing on the shield of the audio cables. So you can see the ferrite chokes in the first picture, open and closed. you close them around the wire, or you can actually wrap them if it's a big enough choke, big enough ferrite, you can wrap it 2 or 3 times through there to give 2 or 3 times the performance. Reduces the RF flowing on the shields of the cables, the outside of the cables. A low-pass filter. Low-pass filter is a filter used between the transmitter and antenna to eliminate harmonic emissions. They're called low-pass because you want to transmit your signal through, but eliminate all the higher frequencies that might jam a television. More interference killers. Here's a smaller, simpler one. This one you might use at the TV. This doesn't handle the hundreds or thousands of watts that your transmitter might put out, but it's only to protect the TV. You put that in line with your television antenna connection. It's a band reject filter. It rejects any band that's not a television frequency. It helps prevent overload from nearby transmitters. Doesn't take out all the signal, but it knocks it down far enough to help prevent overload. Again, the term there is called band reject filter. Grounding helps too. Flat strap is best. Connect all equipment to a common ground. In your car, the common ground would be the engine. It might also be the body of the car. But all of those should be bonded together to help give you maximum shielding from any engine noise or engine ignition or computer noise. But flat strap is best. Connect all equipment to a common ground. Car installations, the radio ground can be a connection to your radio chassis or engine block. I'm sorry, the car chassis or the engine block. Bond all the grounds together. For example, if your hood needs to be grounded, it has nylon rollers on the hinge. It has a good deal of paint on it. If your hood needs to be grounded, it's not grounded automatically. You have to add some of that ground where it's needed. If you really need to block some of the engine ignition noise. More car installation tips. Your power supply should go directly to the battery or to an unused fuse box terminal. Try not to share it with other terminals. If you go to transmit and it shuts off your engine computer, that's not good. So if you're going to use the fuse box terminal, make sure it's unused. You're not sharing it with something else, so you don't blow a fuse that's needed for the car. Alternator, noise and whine. You can tell it's an alternator whine because it varies with the RPM of the engine. And for alternator noise, filters do help. Picture of one on the right there. Ignition noise. Ignition noise is pulsing or ticking noise. And the noise blanker in your radio. This thing called NB level is noise blanker. And then there's an NB2. That's the second noise blanker. Many of your receivers can help filter out those pulsing noises. Operating controls. Right. Operating controls, RIT is receive incremental tuning. It's used to fine tune the receive frequency, not the transmit frequency, sometimes called the clarifier. Helps if a SSB signal is high or low pitched. In other words, if you're talking to somebody whose radio is not exactly on the same frequency as everyone else, you might switch in the RIT when that person is transmitting. If he sounds too high or too low for a normal voice, the RIT helps to shift that. AF, Audio frequency gain. It's just a fancy name for the volume control. AGC, automatic gain control, keeps received audio relatively constant. So you don't always have to turn the volume up and down. They're helpful most of the time, not all the time, depending on how crowded the band is. They are helpful. RF power output. There's a power control there, sets your power output. Microphone gain sets your microphone gain. It says too high or too low, and your signal will be distorted. Or I'm sorry, too high, and your signal will be distorted. You want to make sure that your audio is nice. If it gets too high and sounds a little distorted, it's going to occupy a lot of bandwidth and annoy everybody else on that band. So you're supposed to keep your signal clean, and the microphone gain is what helps you do that. And RF gain. RF gain is receiver gain. Received radio frequency gain is called RF gain. Squelch mutes the receiver when no signal is being heard. Don't set it too high or you'll miss weak signals. Also, squelch is only typically used on FM signals because sometimes the noise background overrides what you want to squelch. So, but the squelch mutes the receiver where no signal is being received. Don't set it too high or you'll miss the weak signals. That's part of the quiz. It doesn't always work, but that's not what the quiz wants to know. Operating controls. The HF transceivers often have a selection of filters permits noise or interference reduction by selecting a filter bandwidth that matches the mode. For example, a filter made for 2400 hertz would be good for sideband. 500 hertz would be good for CW. So in your operating controls on your radio, you can select different filters if they're installed. Not every radio comes with all these filters installed, but many of the newer radios, they're included as a function inside, so you can set those frequencies. For example, remember I said that 300 to 3000 is a typical voice range? Well, on sideband, if you cut it back to 2400, you can still hear most of that 3000 hertz, and you don't have to listen to the neighboring frequency where somebody might be splattering a little bit more than 3000 hertz. And the operating frequency is the big dial. It's set by the VFO knob or by a keypad entry. So in general, the VFO knob is good, but you could also dial in the frequency exactly if you know it and your radio has a keypad direct entry. Favorite frequencies can be stored in memory for easy access. So that's good. Operating controls. Operating controls on radios. This one here is just about like that one there. I think I have an F6 and that's an F7, very similar controls. Let's see. The offset frequency. When you're operating on a repeater, you have to use an offset frequency. And that is, in this case, is called the shift, offset or shift frequency. Difference between what you transmit and what you receive. The REV control, just below that, REV control is a reverse control. You can reverse your frequencies. So you can hear somebody, if you're close enough to somebody, you can hear what he sounds like before he goes into the repeater. You can talk to them back. If you're out of range of the repeater, and both of you are out of range of the repeater, you can talk to each other one guy goes in the reverse mode, reverses those frequencies, and your transmit and received are reversed, and you don't need the repeater at that point. Station equipment. The basic pieces are a transmitter and receiver. Used to come in 2 boxes. Nowadays, there's no need to have 2 boxes. You can put the transmitter and receiver all in one. It's called a transceiver. The antenna is switched between transmitter and receiver internally. Put one antenna in there. When you push to talk, it switches from receive to transmit. RF power amplifier. The increases your power. The RF amplifier can be increased by this blue box. That's the size and shape of most VHF and UHF amplifiers. Amplifiers for the HF bands very often are bigger than that, with a lot more switches and knobs. But this is a typical VHF power amplifier. Increases your output from your low power device, like my handheld. And it's on there, there's an SSB, a CW, FM switch that sets up the appropriate mode. So you see several switches there. One might be the power to turn on, and the other switch would be to set it up, whether you're talking sideband or FM. There. All right. So as far as equipment goes, you have transmitter, receiver. These are the important details for a receiver. The most important specs are sensitivity, ability to receive a weak signal. So these are definitions that you match sensitivity to ability to detect a weak signal. That's the correct answer. Selectivity, in order to select the difference between the station you want and the stations that are next door. You need selectivity, ability to discriminate between multiple signals. An option that's typically included in modern radios is a preamplifier. It helps to amplify the weak signals. It's installed between the antenna and the receiver. So you can put one external between your antenna and your receiver, but sometimes it's also built into modern radios. The internals of a transceiver include a mixer, converts radio signals from one frequency to the other. Mix the frequency, mixes your 2 frequencies, one that you want and one that you need to shift it somewhere else where the equipment is better able to handle it. An oscillator circuit generates signals at a specific frequency. It can be fixed, it can be variable. You could be shifting the oscillator with the big knob on the front of the radio, but it could be fixed. It could be an oscillator at a specific frequency that doesn't move. Modulator combines your speech or other intelligent signals with an RF carrier. This modulator is often made of a different type of mixer. So you mix the audio and the RF together, and it becomes a modulator. Sometimes that function can be done by a mixer. Transmitter functions. Transmitter function here looks like an AM transmitter. Many of the components are the same. The modulator turns out to be different. So the RF is generated by an oscillator. Oscillator goes into a buffer amplifier to make it more powerful. Your AF, audio frequency, comes in your microphone, goes to a speech amplifier, goes to a more powerful driver, so that when they mix together in the modulator, you come out with an AM signal. Go through a power amplifier to make sure it's powerful enough to be heard on the other end through your antenna. And there's the diagram of the amplitude modulated signal. Voice modes like SSB, single sideband, and FM need a modulator. A modulator combines the RF carrier and the audio or speech signal. A transverter. A transverter is used to operate on a frequency which a radio was not designed for. A transverter is a device that takes the output of a low-powered SSB exciter and produces a 222 megahertz output signal. Now, your 28 megahertz SSB exciter can be say a 5-watt or a low-power signal coming from a 10-meter radio. Now, 28 megahertz is 10 meters, which you could have laying around because the sunspots means you don't use it very much anymore. You run that through a transverter, and now you're on the 220 megahertz band, 222 megahertz band, which is more useful. It also converts the incoming, the received signal, 222 megahertz, to the 28 megahertz signal for your receiver. So the transverter, again, is in the middle sentence, the italics and the bold letters. Some UHF and VHF info. Most operation is using FM and repeaters. CW and SSB are also popular, often for weak signals. Weak signals are something that aren't necessarily weak by nature, but because you go so much further with those two modes, you often put up with the weaker signal. The device most useful for VHF weak signal communications is the multi-mode VHF transceiver. Multi-mode means FM, CW, and SSB, all in one transceiver. Handheld transceivers, HTs, have low power, 5 watts or less, which limits the range. The device that increases the low power from these transceivers is an RF power amplifier. Once again, I've used handy talkies in my cars for years with an amplifier in the trunk. Either it's 5 watts or 100 watts, depending on how much signal I need at the time. So that device is called an RF power amplifier. Increase the low power to a high power. Troubleshooting common problems. Problems are overload, distortion, feedback, and interference. What can cause radio frequency interference? Fundamental overload. Fundamental overload means that there is a signal so close and so strong that it distorts your radio. You can't separate the signals anymore. Harmonics. Most ham bands are harmonically related. So you can get interference if you're operating on the 40-meter band and somebody is distorted on the 80-meter band. That's a 2-to-1 frequency ratio. Harmonics coming from something usually unintentional, but something that should not occur on a clean station. Harmonics can cause you interference. And spurious emissions. Spurious emissions come from electronic failures. in somebody's transmitter. It doesn't have to be a ham transmitter. It can be police transmitter. It can be other devices up on the same tower as the repeater you're trying to use. Any of these can cause radio or television interference. Now, if someone tells you your transmissions are causing interference, you should first make sure your station is functioning properly, not causing interference to your own TV and radio. Telephone interference. Telephones often experience interference. Most likely, the cause of interference to a non-cordless telephone. Non-cordless telephone, that's a telephone with wires, from a nearby transmitter is that the telephone is acting like a radio receiver. Logical first step is to cure all radio interference on a telephone is to install an RF filter at the telephone. Those would be available in some electronic stores. Now that Radio Shack is gone, radioshack.com is still available. And of course, there are many other places where you can buy them online. So install the RF filter at the telephone. The problem goes away, your neighbors are happy.
Hey, Pat,
Broadcast. Yes.
let me just interrupt for a second.
Go ahead.
Yeah, just real quick, I just want to let you know, I got a message from John, the VE coordinator, that our counterpart in Hawaii, who is basically running our sessions and coordinating the sessions, just woke up because it's 6:25 a.m. in Hawaii, but he is now processing all of the registrations that were done this morning. So everything should be good to go. John will be meeting up with Joe in about a half an hour to make sure everything is good to go. But just to let you know that those who registered today, they're being processed right now. Sorry, Pat, go ahead.
Well, that's very good news. Let's see. And our contact in Hawaii is also named Joe, as is our next speaker. Okay. So, broadcast, AM and FM TV interference. So if you're operating your transmitter and a guy with a baseball bat comes through your window and said, stop that, it's likely that you've interfered with his, with the game he was watching. So.
Hey, Pat.
Yes?
Question, was this really more true when you're using broadcast TV as opposed to cable? Over?
Yes, it's mostly. Cable TV is not supposed to pick up outside signals because they use shielded cables. But there are many times when those shielded cables get broken. Many people trying to make illegal taps that they're trying to share cable signals, and it's not done properly. So your signal can get in and out of the cable by some incorrect hardware that people attach to their cable system.
Yeah, the other issue is that a lot of the old VCRs and even some of the old cable box converters use channel 3 as the input to the TV, and channel 3 is actually very close to our 6 meter band frequencies. So that's where a lot of the interference would come from. But it's true that it's not as prevalent today as it was back when all of our TVs had antennas.
Okay, I didn't realize that it was close to the 6 meter band. That's good to know. Thank you.
Yeah, the 6 meter band is 50 megahertz and channel 2 is 54 megahertz. Channel 3 is also just a little bit close to make sure that all the equipment is going to reject it. It might not reject it because their frequencies are too close. Anyway, it's caused by the receiver unable to reject the strong out-of-band signals. You can eliminate it by installing a filter to block the amateur signal. That is You try to put the filter on your neighbor's television, but that takes some diplomacy. First, you should be sure that you don't generate interference. One way to do that is to put a low-pass filter on, as we showed earlier. Useful ways to cure the RF interference is make sure all TV coax connectors are installed properly. You could snap on ferrite chokes. You could use low pass and high pass filters. You could use band reject and band pass filters. We saw examples of all those things earlier, but proper TV coax connectors, even from cable systems, must be tight and done properly. Fundamental overload is interference caused by very strong signals injected into a receiver. So those filters may not eliminate your signal, but they may cut the signal down well enough to solve the problem. Part 15, devices. If a neighbor's device is causing interference, work with them to identify the offending device. Politely inform them about the rules that require them to stop using the device if it causes interference. And check your station to ensure it meets the standards of good amateur practice. So those are some of the recommended methods in italics that you'll have to put back on the test. You can see the box up top that shows the FCC statement. This device complies with part 15 of the rules, et cetera, et cetera. Common problems: distorted or noisy audio. Your transmitter might be slightly off frequency. Your batteries might be running low. You may be in a bad location. Garbled, distorted, or unintelligible transmission. When it sounds really bad, that could be due to RF feedback. Your transmitter is feeding signals back into your microphone. Could be a broken shield connection on the microphone. Could be RF in the shack. In other words, your signal doesn't go straight out to the antenna. A lot of it's lost in the shack next to your microphone. Or over deviation. Here we go again. Over deviation on FM. Simple solution for that is to back off the microphone. That often comes when you operate in the car. Background is noisier, you shout. You might have people ask you to back off the microphone. Noise in digital transmissions causes bit errors. The term called BER, bit error rate. That's the rate at which errors are occurring. The numbers look very, very small. If you have a bit error rate that's a very small number, it may be tolerable, but anything approaching 1%, and that causes bit errors, causes slow transmissions or failure to connect. High-pitched whine, noise from the vehicle's electrical system, usually the alternator. It varies with the speed of the engine. The alternator is the likely cause. Sometimes that can be fixed. Sometimes the alternator should be replaced. It's on its last legs. Sometimes it needs to be replaced to eliminate that whine. Using a multimeter or DMM. DMM stands for digital multimeter. Multi because it has a voltmeter, an ohmmeter, and an ammeter. Digital multimeter, instead of a needle, it has digits. Measure voltage and resistance. They are a common use. To measure voltage, the voltmeter is placed in parallel with the circuit, as shown in the middle picture to the right. Make sure that the voltmeter leads are rated for the voltage you are measuring. A good set of leads, not necessarily the free meter you get from Harbor Freight, but a good set of leads are rated for about 600 volts. You don't try to measure somewhere in your transmitter 6,000 volts. The leads must be rated properly, or you could get a shock, you could do other damage. And to measure current, the ammeter must be placed in series with the circuit. You have to break the circuit, insert the ammeter, and make sure that your connections are strictly for the ammeter. You can see the difference between the two different connections there. One is for volts, one is for amps. You have to be hooked up differently. And if you do it wrong, you blow the fuse or burn up the meter. So measure current is not done as often, so you got to be careful. Ohm meter. Ohm meter is used to measure resistance. Make sure that the circuit is not powered. You have to measure the resistance of a dead circuit. No power attached. You also can damage your meter. Attempting to measure voltage on the resistance setting might damage the meter. When measuring resistance, an initial low reading that slowly increases means that the circuit contains a large capacitor. In other words, whenever you're taking resistance readings, you would like it to stand still. If it keeps moving, it might be that there's a capacitor in the circuit that you're trying to measure. And soldering. Soldering is a good skill to have. Solder repairs a lot of connectors and connection joints. Rosin core solder is best for radio and electronic use. When you do that, the joints should be shiny and smooth, like the green check mark shows. Dull or grainy surface is a characteristic of a cold solder joint. Cold solder joint means that before the thing cooled down smoothly, you might have moved it. You might not have had enough heat to get a smooth flow to begin with. And that cold solder joint, grainy surface is likely to break loose again. It's not a good connection. Now, this is basic hand soldering. You see someone using solder in his bare hands, you really should use gloves, rubber gloves, plastic gloves when you're soldering with lead. Most of the solder that we like to use is lead. Lead is easier to use, but whatever metals are in the solder, you don't want them. You don't want them on your hands, and you certainly don't want to eat after you've been using this. So there are several grades of solder. Most of them are non-lead solder these days. The non-lead solder is a little bit more difficult to use, but in any case, the questions on the test say to use rosin core solder, to use a dull or grainy surface is a characteristic of a cold solder joint. So these are the correct answers. Exactly how you use non-lead solder is for another day.
All right, and Joe, you're good. You're on slide 129 now. You're good to go.
Okay. Okay, so we're going to talk about operating procedures and advance. First, the duplex and simplex terms. Duplex communications refers to transmit and receive on two different frequencies, where the transmitter on the left would talk to the receiver on the right on one frequency, and the receiver on the right would talk back to the receiver on the left on another frequency. This is going to be important in terms of repeater operation. Simplex communications refers to transmit and receive on the same frequency. One guy transmits, the other guy listens, and then they reverse the process on the same frequency. And on 2 meters, the national simplex frequency is 146.52. And on 450, the 70 centimeter band, 446.0 megahertz. Those are important to remember. Okay, as far as some common transmitter controls on VHF, UHF radios, the carrier squelch, which mutes the audio until an RF signal comes up of sufficient amplitude to open the squelch, and it eliminates the requirement to turn the background noise or turn the volume control down. Essentially, the volume control would be turned up. When there's no carrier, you don't hear the background noise. When there's a carrier, you hear the voice transmission. The other one common is the microphone gain, which changes the amplitude of the modulating signal. In the case of FM, it sets the deviation, and if the deviation is increased, the signal occupies more bandwidth. Okay. Repeater operation. Normally repeaters are located very high, and of course they're either on mountaintops or tall buildings and tall towers. The purpose is to extend the line of sight between two stations located on the ground, whether they're mobile or handheld. And looking at the diagram, you have a repeater input where you talk to the repeater on one frequency. It repeats what you just transmitted at the same time to the on a lower frequency, in this case. And both the input and outputs on the mobile need to be on the same channel pair. So you listen on one frequency, it rebroadcasts on the output. Your radio must transmit on the input and it must receive on the output. And the difference between the input and output frequencies is referred to the split. Okay, station classes that could retransmit signals automatically include the repeaters, auxiliary stations, which are stations that would provide, in the case of a repeater with multiple receive locations, they would provide the link back to a central unit. That if you do have a multiple input system, the system will determine where your which receiver you're using has the strongest signal and puts that back out on the common output frequency. And space stations, satellites. Common splits for the 2-meter band are 600 kilohertz. There are others, but the most common is 600 kilohertz. And on 450, the 70 centimeter band, 5 megahertz. Something to be aware of are repeaters that are actually sharing input and output splits with others that are located tens to hundreds of miles away, but could cause co-channel interference. So we use what's called the continuous tone coded squelch system, or a digital coded squelch to set up one repeater system so that it doesn't interfere with the other one. So there's subaudible tones that are set with your voice to open the squelch, and also referred to as PL tones, which is a trade name that Motorola used. You may hear the term quiet channel that was used by, I think, RCA at one point, but the PL is most commonly used. And the reason why you can hear a repeater but may not be able to open it is because of an improper transceiver offset. The continuous tone coded squelch may be the wrong frequency. I believe there are around 50 of those that are used, and a lot of the equipment is it's a menu setup where the repeater may require a digital tone sequence for access, which is similar where you use a digital encoding scheme to open the squelch. And if a signal is not strong enough to open the squelch, you might be able to hear it by listening on the repeater's input frequency. That's in one of the test questions. And if your signal is breaking up, you may be, again, over-deviated or talking too loudly, and you can remedy that with a reduced mic gain setting. Okay, repeater operation. To strike up a conversation. The term CQ is not really used in repeater work. You just drop your call sign and indicate that you're listening. For instance, W2AEW listening. And if somebody hears that, they'll return their call sign with yours, or call you and return their call sign. And if you hear somebody drop their call, you return with their call sign and identify your transmission with your call sign. Okay, pretty straightforward. In HF operations, CQ is generally used, and good practice is always listen first. You don't want to step on somebody else who may be using that frequency. After you listen for a minute or two, make a transmission and ask if the frequency is in use. And if it is, somebody will come back and say, yeah, it's in use, and you end up moving off. And you also want to make sure that you're operating in a band that's assigned to your class of license. Responding to a CQ signal, just transmit the other station's call followed by your own call. Station identification is always required, even when you're testing. And you want to identify at least every 10 minutes while you're operating and at the end of your conversation. And it's normally this is and your call sign. Technicians can operate CW in 80, 40, 20, 80, 40, 15, and 10 meters. And you'll hear common Q signals that were actually a holdover from the Morse. QRM indicates you're getting interference. QSY indicates you're changing frequency. There are others, but and they are spoken. They are used as spoken shorthand as well as on Morse code, so it's common to hear those. Oops. The general guidelines, the band plan is voluntary for different modes and activities in the amateur band. The bar below is a layout of the 2-meter band that shows CW down in the very lower portion, a single sideband. Some miscellaneous modes, APRS that was mentioned previously. Repeater inputs and repeater outputs with digital packet in there as well. And common practice is to maintain minimum power necessary to carry out the desired communications. You're allowed to 1,500 watts on VHF and above, 200 watts on HF with a technician class license. Okay, and you want to make sure that your signal is clean. If somebody reports that you're causing some splatter, you want to check your transmitter for the proper frequency or for spurious emissions caused by overmodulation is a good place to start. If you unintentionally cause interference, then identify yourself and move off to a different frequency. The other tool to use is the phonetic alphabet when trying to convey alphabets and numbers. This is actually the ITU alphabet. It's encouraged by the FCC. It's also used by the aviation people to, in the spoken word, convey the letters of the alphabet and numbers. Public service and emergency use and non-emergency use. The hams are really uniquely qualified to help out in a lot of events. FCC rules still apply when using the amateur radio for the public service purposes, except, and you have to abide by those, except when there's an imminent danger to safety of human life or property damage, and you can use any means necessary for the essential communications to occur. Two services that the amateurs can participate in related to emergency services are the RACES amateur service, which is the Radio Amateurs Civil Emergency Service. They're amateur radio stations that are used to communicate with civil defense officials, and the Amateur Radio Emergency Service. Both RACES and ARES can provide emergency communications. The primary difference is one is related to the government activities, and ARES is an ARRL sponsored organization. They're both common to form nets orchestrated by a net control station. Messages passed during these operations are called traffic, and common mode of operation is to check in with your call sign, remain on frequency in case you're your services are required by the net control station. And just beware that you are you have the message handling and traffic national traffic system. There are both formal and informal networks. It's most important when you're going to pass a message to pass the message exactly as either it's written or spoken, or as you receive it. And always use the phonetic alphabet when appropriate. The formal messages consist of a preamble, which is usually a check of the number of words that are contained in the message, the address, who it's going to, the text of the message, and followed by the signature. Again, with the National Traffic System, preambles used to track the message system as it passes through the network. The check is the number of words or words equivalent. Address is who it's going to, text and signature we've talked about. Net operations, all net communications are generally handled through the net control station and only transmit when directed by the net control station. If you have something that's of emergency in nature, get their attention by speaking the words priority or emergency followed by your call sign. Amateur satellite activities. Amateur satellites are in orbit. They have uplink and downlink frequencies that are often in different bands. In what's referred to as the UV mode, the link from your transmitter up to the satellite is usually on the 70 centimeter band, in the 420 to 450 region, and the downlink back to you is in the 2 meter band. You need license privileges to transmit on the uplink frequency, but you can listen to the downlink frequencies with receivers that are capable of that. Most run in FM mode. Some operate in single sideband CW or data modes. The satellite beacon has got is normally a transmission that's on the satellite that contains information about the satellite, health and status information in particular. And again, anybody can receive this telemetry. What you need to be aware of, though, when operating satellite communication systems, or the frequency change caused by Doppler, the observed change in frequency is going to be noticed due to the motion between the satellite and you. As the satellite is coming towards you, the frequency will go up, and as it's leaving you, the frequency will appear to go down. Spin and fading is caused by slight rotations of the satellite and the antenna system on board. Those are both questions that you may see. When operating with satellites, you don't want to use too much power because you can block access to the satellite by others. And you need to keep an eye on your signal strength. It should be the same as the downlink that you're receiving from the beacon. FM digital packets commonly used. Sometimes it's a store and forward system. Sometimes it's real time. And there are satellite tracking programs available on the internet. There are maps that show the real-time position, time, azimuth, elevation at the start, and the past details. And as well as frequency, the apparent frequency of the transmissions that includes the Doppler, and the orbital elements, the Keplerians, as input to those things. Space station has got some amateur equipment on it. Any technician class license can make contact with those folks when they're in view. Contact is on both the 450 and 2 meter bands, 70 centimeters and 2 meters. And the space station is considered a low Earth orbit satellite. Contesting. Normally, contests are run for specific time periods. Sometimes it's back-to-back, day-to-day. Sometimes it's across weekends, depending on what particular contest you're working. A very popular one is where everybody takes their normal homebound stations and goes to the field, or goes to the field in field day, which is the usually the last weekend in June. Good practice during contesting is to send the minimum required information that the contest uses. Some of them require signal strength, some of them require contest number. It depends on the contest. And you want to be mindful of others on the band whenever you try to join a contest. A lot of the contests use grid location, which is a system that divides the world up into, I think it's 340 major grids and then 100 minor grids in each of the locations. And then those minor grids have subgrids. You'll normally hear grids referred to by 2 letters and 2 numbers. And if you take a close look at the map here, you see that northern New Jersey is mostly in grid number FN20, Fox November 20. More fun activities, special event stations, which are generally given a letter with a number and a following letter, 3-digit call sign. Whiskey 2 Papa would be the special event station that one of the local radio clubs uses for the annual Battle of Princeton special event station. And that's normally in a December timeframe for a couple of days. And often you'll find special event stations for other events that are significant to the amateur radio community.
And on that topic, Joe, for any of you that may have watched or enjoy the show Last Man Standing, know that the principal in that show is a ham, and it's kind of featured in the show. The show is finishing up its last season, and actually the producer of the show is actually helping to organize a week-long special event where there'll be stations around the world that are using KA6 LMS as a Last Man Standing special event that you're encouraged to go listen to and work. So it's just kind of, so these special events could really involve almost anything.
Yeah, very good. Thanks, Alan. Yeah, the other activity that sometimes is held is fox hunt, where a low power transmitter is hidden in some location and makes periodic transmissions, and participants try to find them using direction finding techniques, and they can vary from everything from the directional antennas that you see here that are used for homing types of direction findings, all the way up to multiple element arrays that have a commutated type direction finding system that would display a line of bearing on a computer screen. And you can actually locate those stations with a fairly good degree of accuracy using the directional antennas and the homing technique. In addition, just be aware that there are some internet activities. The Internet Repeater Linking Project, IRLP, uses a voice over the internet to link multiple repeaters together. And you could talk to a repeater here in New Jersey, linked via the internet to someone out on the West Coast. Repeater directory will list the active nodes as well as the online lists and the information. One of the methods used for to dial up a node from your radio to the repeater input, some radios on the back of the microphone will have a touch tone keypad, which is what's known as the DTMF, or dual tone multi-frequency keypad. Those tones are transmitted to the repeater. The repeater and controllers will respond to those tones and complete the dial up for you. Echolink is another organization that links repeaters. You can actually come in from your computer, but you need to register your call sign and provide a proof of license before the Echolink folks will give you your access authorization. And Gateway is the name that is referred to the station that links the other stations to the internet. Okay, moving on to the, any questions so far on the operations? All right, moving on to the rules and regulations. Amateur activity in this country is regulated by the Federal Communications Commission, also enforced by those guys. And it's referred to as Part 97 of the rules and regulations applicable to amateur radio use. And one purpose, and you might see this on the test as well, is advancing the skills in the technical communications phases of the radio art. Okay, and the definition of an amateur radio station is a station in the amateur radio service consisting of the apparatus necessary for carrying on radio communications. Definition of a space station is anything that's flying higher than 50 kilometers above the Earth. The beacon is an amateur radio station that's transmitting comms for the purposes of propagation or related experimental activities. They can be on both satellites and located on the ground in just about any band, whether it's HF, VHF, or UHF. And realize that frequency coordination for the use of those subbands is normally done by a volunteer frequency coordinator. And the volunteer frequency coordinators are selected by the amateurs in the local region, and they recommend the transmit receive channels primarily for the purpose of mitigating interference between other users. Repeaters, we talked a little about repeaters. The formal definition there is an amateur station that simultaneously retransmits the signal of another amateur station on a different frequency. And the auxiliary station definition as well below. Interference, something that is never permitted, and you want to make sure that we're good neighbors and don't interfere with other licensed other licensed users, other amateurs. And the definition of the harmful interference is right up there on the screen. It seriously degrades, obstructs, or regularly interrupts the radio communication service. If the intentional causing of interference is grounds for the revocation of licenses, a commission can impose some fairly hefty fines and in some cases imprisonment if you're found to be causing intentional interference. International Telecommunications Union, FCC is in the US. The rest of the world has their own organizations, and everybody coordinates their efforts through the International Telecommunications Union, which is a UN agency. They do have an office in New York at the UN. The primary office is in Geneva, I believe. Earth is divided into 3 regions. North American stations are in region 2. And again, the ITU deals with worldwide organizations, and FCC operates within their framework. When you get your license, you're going to have some privileges in the bands that are up here on the screen. Be able to use Morse on 80, 40, and 15 meters. CW again on 10 meters, and some limited phone privileges. You're limited to 200 watts maximum peak envelope power on the 10 meter band. Above 50 megahertz, you have all amateur privileges, everything that anybody in any other class has, with the exception of the few novices that are left. You can pretty much operate with up to 1500 watts PEP. The questions relating to the frequency bands. 52525 is within the 6 meter band. It's also the simplex calling frequency on 6 meters. 2 meter band is what you're using when you're transmitting on the 146.52 national simplex frequency. 43350 is authorized up on 23 centimeters, 1296, and 1.25 meters is 223. And again, you have 200 watts on the assigned portions of the HF band and 1500 watts above 30 megahertz. Again, in some cases, we have primary and secondary users in the amateur world. Amateur radios are shared like with commercial operators in the 70 centimeter band, and the in the 23 centimeter band. Sometimes we're the primary users like in the 70 centimeter band. When we're secondary users, you got to make sure that we are not causing harmful interference to primary licensees. If you do find you're interfering with one of the radio location services outside the US, you need to stop operating and take action. Some of the subbands that we need to be aware of is that in 6 meters and 2 meters, CW operation is only allowed in the first 100 kilohertz or 0.1 megahertz of those bands. And some restricted mode subbands for the technician class license are found on 6, 2, and 1.25 meters. When you find a frequency that's clear, you want to check and make sure that you're not operating too close to the band edge. And the reasons for that are your voice transmissions are going to be wider sometimes than just a kilohertz or two away from the band edge, and you don't want any energy to spill out outside the band. And you want to allow for transmitter drift, and as well as the calibration, any calibration error you may have in your transmitter frequency display. Okay, licenses and operating. This is a picture of what the current license looks like on a wooden plat. Call signs in the US are 1 or 2 letters followed by a single number, which is then followed by 1, 2, or 3 letters. 1 by 2 would be Whiskey 2 Zulu Quebec. 2 by 1 would be Whiskey Alpha 3 November. 1 by 3s and 2 by 3, so on. Vanity call signs are available to any license classed amateur, but they need to match the format for your class of a license. Currently, the only new classes of license that are being issued are technician, general, and extra class licenses. Special events call signs we just talked about. And clubs. In order to be considered a club, you must have at least 4 members in the particular organization to apply for a club license. And that is a current test question. Individual logging is no longer required for each one of your transmissions, but you need to keep your records if you're required to do a RF safety survey. You really need to keep that around, as well as keeping your current mailing address up to date. Failure to do that will result in a suspension or revocation, the FCC will take action if the correspondence that they send you for whatever reason may be a return to sender. You can operate as soon as your name and call sign appear in the FCC's Universal Licensing System database. So if you take the test today, as soon as you check on the internet that your call sign has been issued, you can use that when it appears in the Commission's ULS database. The license is good for 10 years. Renewal grace period is 2 years. So after it expires, you have up to 2 years to actually renew the license, but you can't transmit during the grace period. And you cannot transmit until the renewal shows up in that database. Okay, operating outside of the country, sometimes foreign companies will allow it. Some countries have reciprocal agreements. The example there is Germany, but you need to check with the authorities in the country for local restrictions. Operating on international waters, maritime, mobile, legally you can operate on any vessel documented or registered in the US when they're in international waters. This graphic happens to show a cruise vessel, and what I would suggest you do is check with your cruise operator if you're planning on taking your license and equipment on a commercial cruise vessel. Some cruise operators are amateur friendly, some are not. So you really want to check with the cruise operator. FCC authorized and prohibited transmissions. Common sense, good operating practice. You want to not have the obscene or indecent words or language. And what's expressly permitted is music, except when it's incidental to the authorized retransmission of manned spaceflight. You're going to wake up some astronauts with a song, and you're going to retransmit that as a public service or some other reason. You can retransmit the space communications with the music. And unpublished codes or ciphers. You can use codes and ciphers as long as they're published and well known. The only exception to this is when you're transmitting space commands or transmitting commands to a space vehicle or a radio controlled model or craft. No communications with any country whose government has notified the ITU that it objects to such communications. You cannot use the station to make money or be compensated, with the exception of teachers or supporting a teacher incidental to classroom instruction, or the occasional notification that you have equipment for sale. Some organizations have periodic online swap sessions, but essentially making money from the amateur licenses is prohibited. And no broadcasting. And for the purposes of this section, the broadcast is defined as transmissions intended for reception by the general public. The only exception to that is relations to safety of human life, or when you transmit a code practice section, information bulletins or transmissions. These are primarily for the W1AW ARRL folks. What is allowed? Anything that's incidental to the purposes of the amateur radio service. Remarks of a personal character, brief transmissions for the purposes of making your equipment adjustments. But just about everything of a general conversational nature is allowed. Control operator. Station is never operated without a control operator. And who can that be? Well, it's a person who is the primary station licensee, and your grant appears in the ULS database. And or you're authorized as an alien reciprocal operator. That would be a visiting amateur that is recognized by the U.S. to operate here. And it's usually the station licensee. Need to pay attention to the class of control operator privileges. This means that a technician class licensee cannot be a control operator in the extra portion of the spectrum. It's reserved for extra licensees. You need to have your license or be a control operator in a part of the spectrum where your license is valid. Control operator point is required only for transmitting. You can receive as you like, but it's only for the transmit side. You can be designated by the station licensee, and both the control operator and station licensee are equally responsible for the proper operation of the equipment. This could be, case of this would be an operator that's using a repeater where you as the user are equally responsible as the owner of the repeater for the proper operation of the equipment. The control point's defined as the location at which the control operator function is performed. Local control, it's, you are co-located with the transmitting equipment. Okay, remote control would be a control operator not at the station, but can indirectly manipulate the operating adjustments of a station, such as operating over the internet, being able to shut the repeater down if something goes awry with the repeater itself from a remote location. Control operators required to be present at the control point, either indirectly manipulate the controls or locally manipulate the controls. And automatic control is when a repeater when the control operator is not present at the control point. The only permissible type of the control operator to be at location other than the control point. Station identification, again, every 10 minutes and at the end of the contact in English or by voice in the case of phone, or Morse in the case of any other emissions class. Use of the phonetical alphabet is encouraged. The only time you don't have to identify is when you're transmitting signals to a model craft for control purposes. Tactical call signs, like if you're supporting a walkathon or a race operator, are okay, but you still have to give your call sign ID every 10 minutes. More on station identification. This map shows the ARRL call district map, which were the original FCC call districts. And normally what happens with your license is that you're assigned a number. With your initial license will have a number in the district that you're operating. You can change that with a vanity call sign. Just don't conflict with any other FCC identifiers or foreign country call sign prefixes. Third-party comms, that's communications on behalf of someone other than a licensee, like a friend using your station to talk. It's legal between any two stations in the US. If you go overseas, you may have some restrictions on third-party communications. Just make sure that the other country does have a third-party agreement with the US. Again, station records have to be available to the FCC at any time. And that's the end of the show.
So if there aren't any questions, why don't we just jump into doing a couple of practice exams? And I think what I'll do, let me do a share of the web browser. So you should be able to see this this practice exam here. I'll read the questions, and then maybe what I'll do, let me pop up a chat window here. So if you wanted to either, suggest your answer either, by unmuting, or if you want to type your answer into the chat or just watch, that's fine. but let's run through this as if it's a real exam, and we'll take the majority of the answers that I get and answer the questions that way. So this first question, what is the electrical difference between RG58 and RG8 coaxial cable? Is it A, that RG58 can handle higher power? B, there's no significant difference between the two types. C, RG8 has less loss at a given frequency, or RG58 has two shields. So I see a letter C. Anybody, any other answers? There's another C. There's a couple of more C's coming up here. So let's suggest C and see what happens. That's correct. All right. Next question. What type of wave carries radio signals between transmitting and receiving stations? Is that electromagnetic waves, electrostatic waves, surface acoustic waves, or ferromagnetic waves? Looks like the A's seem to have it. Let's select A. There you go. Okay. Next question. What type of tones are used to control repeaters linked by the Internet Relay Linking Project, or IRLP protocol? Is that CTCSS, Echolink, Subaudible, or DTMF? So remember, this is to control IRLP links. I got some A's, I got some D's. I got an even split here. Anybody want to tip the scales one way or the other? A couple more D's coming in. If I put my vote in, we'll also say D. Remember, the CTCSS tones are for squelch. The DTMF tones are for controlling a linking, okay? So what electrical parameter is controlled by a potentiometer? Is it inductance, capacitance, field strength, or resistance? Okay, I see a couple of D's coming in. There's a couple of B's, a B. Looks like the D's are the majority. A potentiometer does control resistance. It's a variable resistor. Okay, what information is contained in the preamble of a formal traffic message? Is that the telephone number of the addressee, the email address of the originating station, the address of the intended recipient, or the information needed to track the message? Okay, it looks like the D's are what I'm getting, and D is correct. As what you'll find with a lot of these exams is that there's usually one answer that's obviously wrong. There's two that are like, well, I could be right. And then there's a one answer that's more right. So let's keep that in mind. So which of the following is an example of remote control as defined by Part 97? Repeater operation, operating the station over the internet, controlling a model aircraft, boat, or car by amateur radio, or all of these answers? Okay, I'm seeing a D. Actually, there's a problem when D was the previous answer. I can't tell when new ones pop up here, but I think I'm seeing D. Still D. Okay, thank you, Chris. Not right. Okay, so let's I guess I want to give a second answer. I see a B. B is correct. Okay. Which of the following is an advantage of HF versus VHF and higher frequencies? HF antennas are generally smaller. Long distance ionospheric propagation is far more common on HF. HF accommodates wider signal bandwidths, or there is less atmospheric interference or static on HF. So Kim says B, as does RP. Let's select B, and that is correct. Okay. Which of the following measurements are commonly made using a multimeter? SWR and power, signal strength and noise, impedance and reactance, or voltage and resistance? Saying D on that one, and that is correct. Okay, what is a symptom of RF feedback in a transmitter or receiver or transceiver? The transmitter will not stay on the desired frequency, excessive SWR at the antenna connection, frequently blowing fuses on your power supply, or reports of garbled, distorted, or unintelligible voice transmissions. Okay, D again. Let's take a look. Absolutely right. Okay. All right, so here's one of the schematic questions. What is the component 4 in figure T3? So component 4 is this guy right here. Is that ground, antenna, dummy load, or transmitter? And it looks like B is the consensus, and that is correct. Which of the following is a result of the fact that amateur radio service is secondary in all or portions of some amateur bands, such as portions of the 70 centimeter band? Is it A, the US amateurs may find non-amateur stations in those portions and must avoid interfering with them? Or B, the US amateurs must give foreign amateur stations priority in those portions? Or D, digital transmissions are not permitted in those portions? Or D, international communications are not permitted in those portions? So it looks like A's have it. So there's the A's. Okay. What is the name given to an amateur radio station that is used to connect other amateur radio stations to the internet? Is that a beacon, a repeater, a gateway, or a digipeater? Okay, I got C's and B's. And we're connecting other stations to the internet. Okay, oh, it's like more C's are coming up here if I count them all up. C, gateway, is correct. What does the abbreviation PSK mean? Packet short keying, phase slide keying, phase shift keying, or pulse shift keying? And I'm seeing a bunch of C's come up here. C is correct. Okay, now who may receive telemetry from a space station? A licensed amateur who has been certified by the protocol developer, a licensed radio amateur who has registered for an access code from AMSAT, or a licensed radio amateur with a transmitter equipped for interrogating the satellite, or anyone who can receive the telemetry signal. And it looks like the D's have it. The D's are correct. Which of the following electronic components can amplify signals? A variable resistor, a transistor, an electrolytic capacitor, or a multi-cell battery? Okay, I got a couple of A's, a couple of B's. Got a couple more B's. So B, transistor, is correct. Which of the following controls could be used if the voice pitch of a single sideband signal seems too high or too low? Is that the tone squelch, the AGC or limiter, the receiver RIT or clarifier, or the bandwidth selection? Okay, I've got a D, a C. Anybody else want to go? There's another C for the receiver clarifier, another vote for the RIT or clarifier. And that is the correct answer. Which of the following is a good electrical conductor? Glass, rubber, copper, or wood? Okay, that one's pretty obvious. That's copper, the only conductor. Now, what's the formula used to calculate voltage in a circuit? Okay, so remember your little circle diagram. Voltage is equal to the current multiplied by resistance. Voltage is equal to the current added to the resistance. Voltage is equal to the current divided by resistance, or voltage is equal to the current minus the resistance. All right, everybody's looking at their little diagram they wrote down and saying that voltage is equal to the current multiplied by resistance, and that's correct. Which of the following is a guideline when choosing an operating frequency or for calling CQ? You want to listen first to be sure that no one else is using the frequency. Ask if the frequency is in use. Make sure you're in your assigned band, or all of these answers are correct. And most people are saying that it is all of these answers, and that is correct. What is an advantage of using a properly mounted 5/8 wave antenna for VHF or UHF mobile service? It has a very high angle for better communications through a repeater. It has 10 times the power gain of a quarter wavelength design. It has a lower radiation angle and more gain than a quarter wavelength antenna, or it eliminates distortion caused by reflected signals. So I've got a couple of C's. And it looks like the consensus is C. It has a lower radiation angle and more gain than a quarter wave, and that's correct. Okay, so what is a relay? A relay is an optical sensor, a pass transistor, an electronically controlled switch, or a current controlled amplifier. It looks like I'm seeing some C's pop in here. And that is correct, electronically controlled switch. Now, how might a computer be used as part of an amateur radio station? For logging contacts and contact information, for sending or receiving CW, for generating and decoding digital signals, or all of these answers? And that is correct, everyone. It's all of these answers. I love the fact that just about everybody's answering all the things correct here. So this is great. Under which of the following circumstances are amateur stations authorized to transmit signals related to broadcasting, program production, or news gathering, assuming no other means is available? So only where non-commercial programming is gathered and supplied exclusively for the National Public Radio Network, only where such communications directly relate to the immediate safety of human life or protection of property, only when using amateur repeaters linked to the internet, or only when broadcasting communications to or from the space station. So I get a couple of B's, a lot of B's, and that is correct. All right, so who may select a desired call sign under the vanity call sign rules? Only a licensed amateur with a general or amateur extra class license, any licensed amateur, only a licensed amateur has been licensed continuously for more than 10 years, or only a licensed amateur with an amateur extra class license. And I'm seeing a bunch of B's, and the B's have it. Any licensed amateur is correct. So which of the following is true when installing grounding conductors used for lightning protection? Wires must be carefully routed with precise right angle bends, or sharp bends must be avoided. Only non-insulated wire must be used, or common grounds must be avoided. Okay, I think I see a couple of B's popping up here. Avoiding those sharp bends is correct. Okay, how can you make sure your station stays in compliance with RF safety regulations? A, by informing the FCC of any changes you make in your station, by reevaluating the station whenever an item of equipment is changed, making sure all of your antennas have a low SWR, or all of these answers. And I see a couple of B's, I see a D. Someone's got to break the tie here. There's another D. And then a couple of more B's. So I think the B's have a slight majority, and the B's are correct. Okay, so what's the name for the distance a radio wave travels during one complete cycle? Is that the waveform, the wave speed, the wave spread, or the wavelength? How far the radio wave travels during one complete cycle? And I got a couple of D's, and the wavelengths have it. Okay, last question. What can happen? Oh, no, it's not the last question. No, it's not. I'm sorry. We're on question number 26. What can happen if a lead acid storage battery is stored or discharged too quickly? The battery could overheat, give off flammable gas, or explode. The voltage could become reversed. The memory effect will reduce the capacity of the battery, or all of these answers. There's a bunch of A's, and the A's have it. That's correct. Okay. Now, which of the following describes combining speech with an RF carrier? Is that impedance matching, oscillation, modulation, or low-pass filtering? And I see a bunch of C's for modulation, and that's correct. Okay, so what type of amateur station simultaneously retransmits the signal of another amateur station on a different channel or channels? Is that a message forwarding station, a repeater station, a beacon station, or an earth station? And I'm seeing a lot of B's for repeater station, and that's correct. What type of modulation is most commonly used for VHF packet radio transmissions? Is that PSK, AM, single sideband, or FM? Let's see, I got a couple of A's and B's. So another A, that's kind of breaking the tie. Any more? I won't call you out. I think the A kind of slightly broke the tie for PSK, but that's not right. Okay, so now I see a C. Okay, so, and I see a D. Okay, someone's got to break the tie between C and D here. Oh, there's another D. FM is correct. The key there was VHF. That's mostly typically FM operation up there. So, okay, which of the following is equal to 500 milliwatts? Is 500 milliwatts equal to 5 watts, 50 watts, 0.5 watts, or 0.02 watts? And I'm getting a couple of C's, a bunch of C's, 0.5 or half a watt. That's correct. All right, what's the formula used to calculate electrical power in a DC circuit? Okay, remember our little formula again, our little pie chart. P equals voltage multiplied by current. Power is voltage minus current. Power is voltage plus current, or power is voltage divided by current. Okay, it looks like I'm getting a bunch of A's. People written down their formula correctly. All righty. Which of the following is the most common cause for failure of coaxial cables? Moisture contamination, gamma rays, velocity factor exceeding 1.0, or overloading? Okay, so I'm getting a bunch of A's for moisture contamination, and that's correct. All right, last question. What is proof of possession of an FCC issued operator or primary license grant? Is that a printed operator or primary license issued by the FCC? It must be displayed at the transmitter site. The control operator must have an operator or primary station license in his or her possession when in the control of a transmitter. The control operator's primary station license must appear in the FCC ULS consolidated licensee database, or all of these answers. Okay, so I got a couple of D's. I got a C. I got a couple more D's. The D is not right. Okay, so which ones? It looks like we're now leaning towards C, and C is correct. All right, folks, very good. You know, all of us as a group, okay, answered 32 out of 35 correct, and you passed with a 91% rate. You only have to get 26 right. So even with those answers wrong, if they were all one person, you still passed. So let's start a new one. Okay, same thing, technician class practice exam. All right, we should get 35 different questions here, pulled from the same pool of 350 questions. So what types of international communications is an FCC licensed amateur radio station permitted to make? Is communications incidental to conducting business or remarks of a personal nature? Any communications that would be permitted by an international broadcast station? Communications incidental to the purposes of amateur radio service and remarks of a personal character? Or only communications incidental to contest exchanges or other communications are permitted? But I'm getting a lot of C's. So let's go pick C, and that is correct. What's the proper abbreviation for megahertz? Little m hertz, big M hertz, big M little hertz, or big Z? And the answer is B. All right, capital M for mega, and it's capital H for hertz because that's the guy's name. All right, which of the following connectors is most suitable for frequencies above 400 megahertz? Again, above 400 megahertz. A UHF or a PL259 connector, a DB25 connector, an RS213 connector, or a type N connector. All right, I got a couple of Ds. The N connector is correct. What is a beam antenna? An antenna that concentrates signals in one direction. An omnidirectional antenna invented by Mr. Clarence Beam. An antenna built from aluminum I-beams, or an antenna that reverses the phase of received signals. Looks like I got a bunch of A's, and that's correct. What is the resistance of a circuit that draws 4 amps from a 12-volt source? So we're looking for resistance, 4 amps from a 12-volt source. Is that 3 ohms, 48 ohms, 16 ohms, or 8 ohms? And I'm getting a lot of A's. 12 volts divided by 4 amps is 3 ohms. That's correct. Which of the following describes the Radio Amateur Civil Emergency Service, or RACES? Is that a service using amateur frequencies for emergency management or civil defense communications? A radio service using amateur stations for emergency management or civil defense communications? An emergency service using certified by the Civil Defense Organization as being enrolled in that organization, or all of these answers are correct? Let's see. I don't know how many of those A's are new A's or old A's, and I got a D. Looks like the A's have the majority, so that's not right. Okay, so what else do you say? The D was the other answer we saw, and that is correct. Okay, what's the difference, or excuse me, what is the definition of duty cycle during the average time, excuse me, right, I'm getting tongue-tied, sorry. What is the definition of duty cycle during the averaging time for RF exposure? Is that the difference between the peak envelope power and average power of the transmitter? The difference between the lowest output power and the highest output power of a transmitter? The percentage of time that a transmitter is transmitting, or the percentage of time that the transmitter is not transmitting? I see a bunch of C's, and that is correct. Which of the following is a likely cause of irregular fading of signals received by ionospheric reflection? Is that a random combining of signals arriving via different paths, interference from thunderstorms, intermodulation distortion, or frequency shift due to Faraday rotation? Let's see, I see a couple of C's. I see an A. I see, what was another A? Oh, another A, another A. I think the A's have it. Random combining of signals arrive from different paths, and that's correct. What device converts the RF input and output of a transceiver to another band? Is that a high-pass filter, a transverter, a low-pass filter, or a phase converter? Oh, I see a bunch of B's. A transverter. That is correct. Which of the following could you use to cure distorted audio caused by RF current on the shield of a microphone cable? Would that be a ferrite choke, a preamplifier, a low-pass filter, or a bandpass filter? And I'm seeing a couple of A's as a ferrite choke. No one's changing my mind, and that is correct. Okay, under which of the following circumstances may an amateur radio station make one-way transmissions? A, at any time as long as no music is being transmitted. Or B, when transmitting code practice, information bulletins, or transmissions necessary to provide emergency communications. At any time, as long as the material being transmitted did not originate from a commercial broadcast. Or D, under no circumstances. So I'm getting a couple of B's, and the B's are correct. Transmitting code practice, information bulletins, or transmissions necessary to communicate for emergency. All right, what type of modulation is most commonly used for VHF packet radio transmissions? Well, we just had this question, so hopefully you'll remember this one. Is C. We just had this question in the previous exam. So it's randomly generated. Sometimes you randomly grab the same question. Which of the following is an important safety rule to remember when using a crank-up tower? This type of tower must never be painted. This type of tower must never be grounded. This type of tower must not be climbed unless retracted or a mechanical safety locking device has been installed, or all of these are correct. Let's see, I see a bunch of C's, not to climb it unless it's retracted, or safety devices, and that's correct. What's another way to specify a radio signal of 1,500,000 hertz? Is that 1,500 kilohertz, or 150 kilohertz, 15 gigahertz, or 1,500 megahertz? And I see a couple of A's, 1,500 kilohertz, and that is correct. All right, which of the following is an example of automatic control? Is that controlling the station over the internet, or repeater operation, or using a computer or other device to send CW automatically, or using a computer or other device to identify automatically? See, I see a B, there's another B, and another. Repeater operation is correct. All right, which of the following effects might cause radio signals to be heard despite obstructions between the transmitting and receiving stations? Quantum tunneling, Faraday rotation, Doppler shift, or knife edge diffraction? Looks like I've got a whole pile of D's for knife edge diffraction, and that is correct. But what is meant by the term check in reference to formal message traffic or traffic message? The value of a money order attached to the message, a box on the message form that indicates the message was received and or relayed, the number of words or word equivalents in the text portion of the message, or a list of stations that have relayed the message. Let's see, we got a couple of C's, and there's another C. The number of words is correct. What instrument other than an SWR meter could you use to determine if a feed line and antenna are properly matched? Use a voltmeter, a directional wattmeter, a iambic pentameter, or an ohmmeter. And I see a couple of B's for a directional wattmeter, and that is correct. Which of these components can be used as an electronic switch or amplifier? An oscillator, a potentiometer, a transistor, or a voltmeter? And I see a couple of votes for C, the transistor. That is correct. Okay, which amateur radio stations may make contact with an amateur radio station on the International Space Station using 2 meters and 70 centimeter band frequencies? So only members of amateur radio clubs at NASA, any amateur holding a technician or higher class license, only astronauts' family members who are hams, or contacts within the ISS are not permitted on amateur frequencies. And I got a pile of B's for any amateur holding a technician class license, and that is correct. What telemetry information is typically transmitted by satellite beacons? The strength of the received signals, the time of day accurate to plus or minus 1/10 of a second, the health and status of the satellite, or all of these answers are correct. Let's see, I see some D's and some C's. There's some more D's. So let's see, is it all of these answers? Nope. What's your second guess? Yep, C, health and status of the satellite is correct.
Could you tell us what is not right here, so it also helps us?
Yep, I'm sorry, yep. Yeah, so that one, what was not right was, I can't go back unfortunately, but it was the health and status was the one.
Awesome.
Yep, okay.
If you just do that for all the questions, I appreciate it.
Oh yeah, no problem, yep, okay. All right, so another schematic question. I've got component 2, that's this guy right here. What is that? Is that the indicator lamp, the connector, the resistor, or the transistor? Okay, so I'm seeing D's. So in that case, that would be the transistor. And that's right, because 1 is, that's a resistor, 3 is a lamp, 4 is a battery, 5 is chassis ground. All right, so number 2 is the transistor, number D. Okay, what is the correct way to connect a voltmeter to a circuit? Is that connected in series with the circuit, in quadrature with the circuit, in phase with the circuit, or in parallel with the circuit? Okay, so a voltmeter, we always want to connect in parallel with a circuit, so that's D. In series is what you do with an ammeter, and these other two don't make any sense. So in parallel with the circuit is correct. Okay, which of the following is a good electrical insulator? Okay, an insulator, is that aluminum, copper, glass, or mercury? Okay, so we're looking for an insulator. Remember, an insulator is one that does not conduct electricity. Okay, so aluminum and copper and mercury are all metals, so they do conduct electricity. So the only one that's an insulator is C. As most people have answered, that's correct. Okay, which Q signal indicates that you are receiving interference from other stations? Is that QSB, QTH, QRM, or QRN? Okay, so I see a bunch of letters for C. Remember, QRM stands for man-made interference. Okay, so that one is correct. QSB is fading, QTH is your location, and QRN is natural noise, like atmospheric static. So QRM is correct. Now, what is the approximate velocity of a radio wave as it travels through free space? 300 million miles per hour, 300 million meters per second, 150,000 kilometers per second, or 150,000 miles an hour. Okay, and the consensus here is 300 million meters per second, and that one is correct. Okay, which of the following formats of a self-assigned indicator is acceptable when identifying using a phone transmission, with your voice? Like KL7CC stroke W3, KL7CC slant W3, KL7CC slash W3, or all of these answers are correct. And the answer is that all of these are correct. They're just different ways of saying the same thing. So D is the correct answer. All right, which of the following is an appropriate receive filter bandwidth for minimizing noise and interference for a single sideband transmission? Is that 5,000 hertz, 2,400 hertz, 500 hertz, or 1,000 hertz? I'm seeing a bunch of answers for B, which is 2,400 hertz, and that is the right answer. Most phone transmissions are in the neighborhood of 2,000 to 3,000 hertz wide, so that's a good answer. This would 5,000 hertz would be too wide. These others would be too narrow for voice transmissions. So the 2,400 hertz would be a good narrow filter for single sideband. Okay. How should you respond to a station calling CQ? Transmit a signal report followed by your call sign. Transmit CQ followed by the other station's call sign. Transmit the other station's call sign followed by your call sign, or transmit your call sign followed by the other station's call sign. Okay, so I'm seeing a couple of C's and D's. So it's certainly not A, right? Because you're not going to give them a signal report to establish a communication. And you're not going to transmit CQ because that's if you're trying to call somebody. If you're trying to answer somebody, you don't do that. So it definitely comes down to C or D, right? And actually the proper answer is that you want to send your call sign or send the other station's call sign, then yours. So that way they know that you're calling them and they can listen up for your call sign. So C is the right answer. You transmit their station call sign first, and then your call sign. All right, which of the following methods is used to locate sources of noise interference or jamming? The Doppler radar, echolocation, phase locking, or radio direction finding? Okay. Well, Doppler radar doesn't seem to make much sense. Echolocation, we're not bats. Okay. Phase locking doesn't make sense for direction finding. So D, as most people have answered, is what we do. Which of the following may be included in packet transmissions? A checksum that permits error detection, a header that contains the call sign of the station to which the information is being sent, an automatic repeat request in case of error, or any of these answers, or I should say all of these answers are correct. So certainly Pat talked about a checksum, and these other pieces of information could be in there as well. I see most people looking for all these answers, and we think that's right, and it is. All right, which of the following is a safety hazard of a 12 volt storage battery? Touching both terminals with your hands can cause an electrical shock. Shorting both terminals can cause burns, fire, or an explosion. RF emissions from the battery, or all of these answers are correct. Well, the battery itself doesn't emit anything on its own, so that kind of eliminates two of those answers. It looks like the consensus is B, that shorting the terminals can cause burns or fire or an explosion, and that is correct. What type of electrical component consists of two or more conductive surfaces separated by an insulator? Is that a resistor, a capacitor, a potentiometer, or an oscillator? Okay, I see a couple of Bs voting for capacitor. And that is correct. A resistor resists electrical current. A potentiometer is a variable resistor. An oscillator is a circuit that produces a signal. A capacitor is the electrical component with two conductive surfaces separated by an insulator. All right, what type of circuit controls the amount of voltage from a power supply? Is that a regulator, an oscillator, a filter, or a phase inverter? All right, so I'm seeing a bunch of A's. Well, we didn't talk about anything called a phase inverter, so we can eliminate that. Filter doesn't sound like it has anything to do with controlling the amount of voltage. And we just mentioned what an oscillator is, so it must be a regulator, and that's correct. All right, last question. What is a Part 15 device? This is an unlicensed device that may emit low-power radio signals on frequencies used by a licensed service, or a device for long-distance communications using special codes sanctioned by the IARU, or a type of test set used to determine whether a transmitter complies with FCC type 91.15, or an amplifier that has been type certified for amateur radio. And some of these obscure laws, but this is indeed an unlicensed device that may emit low-power radio signals on frequencies used by a licensed service. All right, we did 33 out of 35. So again, we only had to get 26 right. So we're good to go.